No, it's not going to record locally. I actually found out how to do the stream. So we're going to do the stream.
好呀。那你下周那你就不参加了，好不好？
我听他们说了。
行啊，挺好的，拜拜。大家都老年痴呆症的感觉，呆呆的。
Why there's some noises?
You can mute all the participants.
Okay, let me mute some participants. Mute. Let's see.
You can mute all.
Yeah.
I have a question.
Oh, I mute the question now. I'm sorry. Who has the question?
You have to unmute yourself. Anybody want to speak, you can unmute yourself first. Hello? Yeah. So can you hear me, Chen Chang?
I can hear you.
Okay.
Yes, we can hear from you.
Yes. Hello. There's some question in the talk asking for PDF PDF of the slides.
Maybe later, because I'm still updating my slides. Maybe after my 3 lectures, I can give you a complete PDF file.
Okay.
Well, the point is that if you make a definition, and I forgot the definition, and you are ahead, then it's much easier to just go back. So I don't worry if the version is not complete.
Okay. How do I share? I do have it, but how do I share the file?
I think in the chat you can just you can upload a file.
That with the chat. Okay. But I don't have the chat here. Okay. Oh. Let me share the talk, and I think I can do it.
Thank you.
Okay, I think the files are shared. So should we start?
Yeah, let's start.
You might want to turn off the annotation too for that we don't get zoom bombed.
Hello, Chen
Hello.
Chang.
Yes.
Do you want to say something before I start?
It just start. I think it's fine.
Okay, yeah. Okay, maybe, sorry, let me just start. So this is first of the 3 lectures on topological order and its relation with a higher category. So condensed matter physics and the higher category theory is two very different fields. And so at the beginning, it's hard to imagine these 2 very different fields have any relation. One is about the materials, another is quite abstract mathematics. And because these 2 fields develop very independently, so the way we're thinking of 2 fields also very different. So to explain their relation, first, let me try to explain a little bit the way we're thinking in these 2 fields. And in condensed matter physics, in condensed matter physics, we have we define, at least in theory, we define our system using so-called microscopic lattice model. And then using microscopic lattice model, we make all kind of calculation and prediction and experimentalist measure those macroscopic property of those lattice model. So that's kind of a paradigm in condensed matter physics. So therefore, in condensed matter physics, the concept is defined in 2 ways. Some of them are some concepts defined in terms of microscopic lattice model. Other concepts are defined via macroscopic property, in terms of experimental measurement. For example, like superconductivity is a concept in condensed matter system, and their microscopic definition can be viewed as a boson condensation or electron pair condensation. But the macroscopic definition of superconductivity will be the zero resistance or quantization for vorticity, or this the zero viscosity. Okay. However, in mathematics, the definition of a concept are usually in terms of, so at least in some area, in terms of so-called topological invariant. In physics, the topological invariants correspond to experimental measurement or correspond to macroscopic property. So therefore, in mathematics, the definition of a concept are usually in terms of a macroscopic property or macroscopic concept, not in terms of microscopic lattice model. So there's some tension here. And so actually, my feeling is that when I try to apply higher category theory to condensed matter physics, what I need to do usually is to translate the microscopic definition in term to macroscopic definition. For example, in this lecture, we'll mainly talk about the gapped phase. And the gapped phase is well defined, or more or less well defined in condensed matter physics, but in terms of a lattice model or microscopic Hamiltonian, things like that. And but it's highly non-trivial to define gapped phase in terms of macroscopic property. And in some sense, it's pretty easy to partially define gapped phase using macroscopic property, like in terms of heat capacity. And we have an exponential dependence of heat capacity, you say that's a gap. But this definition is very partial. This definition do not distinguish different gap phase. So actually, a full macroscopic calculation of a gap phase is a unitary fusion N category, it turns out. So to have a full macroscopic definition in terms of experiments that can distinguish different gap phase is highly non-trivial. And when you're thinking about that, it turns out that the answer for this question is a unitary fusion N category or something similar, you know. And that is for gapped phase, to have a macroscopic or experimental definition of a gapped phase, which can distinguish all the gapped phase. And one can also think about a macroscopic definition of a gapless phase. And this is an open question, and which I will not touch too much. I will mainly concentrate on this first part. But the open question and maybe more interesting question is to have a full macroscopic calculation of a gapless quantum phase. And what is the corresponding mathematics? So the sense is that to describe a gap phase, we need a topology, like algebraic topology. And here, maybe we need a geometry. So answer for this maybe is a geometry, but exactly what kind of geometry is, I don't know. Yeah. So, so first, let me try to define some concept which people use in condensed matter physics. The first important one is what is a lattice model. And so actually, people in condensed matter mainly think in terms of a lattice model. So, so let me just introduce that. A lattice model basically is a quantum system. The quantum system are defined by a pair, a Hilbert space and a Hermitian operator acting on the Hilbert space. Okay, but however, as a many-body quantum system or as a lattice model, this many-body have additional meaning. It means that the Hilbert space have a tensor decomposition. So the total Hilbert space is a tensor product of many smaller Hilbert space. And it's convenient to represent smaller Hilbert space by the vertex of a graph. So here we have a graph, and each vertex representing this smaller Hilbert space, which actually have a finite dimension. So the total Hilbert space also have finite dimension if a number of vertex is finite. Okay, and so that's define the Hilbert space of a many-body quantum system. And then we have a so-called local Hamiltonian. This local really means that this Hermitian operator is a sum of many so-called local operator. Like OI, this local operator, this Hermitian operator only act on a single Hilbert space on the site. And OIJ actually act on the tensor product of two Hilbert vector space on the two site I and the site J, this vertex I, vertex J. But then there is some kind of localness in the sense this graph actually have a sense of neighborhood defined by this link. And then this OIJ only act on the neighboring vertex. And certainly we can have operator act on the three vertex and etc. So that's defined the local Hamiltonian. So that's basically the stage of condensed matter physics. That is condensed matter physics study this kind of a quantum system where Hilbert space have a tensor product decomposition. And in terms of tensor product decomposition, this Hermitian operator we call Hamiltonian have a certain localness. Okay. And so this concept is important because without this concept, we don't have a sense of dimension. But once we have this concept of locality and the tensor product decomposition, then we can talk about a one-dimensional quantum system or two-dimensional quantum system or three-dimensional quantum system. So the sense of dimension would come in. And so in these three lectures, I will concentrate on so-called gapped quantum system. Okay, so that's another definition. What do you mean by gapped? The gapped really means that the eigenvalue spectrum, so those horizontal bar is the eigenvalue of this Hermitian operator H. So the eigenvalue spectrum looks like that. So in terms of physics, that's good enough definition. So it looks like that. That means gapped. That's it. But to define that more accurately, what do you mean by looks like that? You know, looks like this. And so actually, the notion of a gap is not a property of a single pair. It's actually a property of a sequence of pairs, where the number of vertex go to infinity. This n is a number of vertex, and in this graph. And then the notion that as we take a limit of n go to infinity, the eigenvalue spectrum of Hamiltonian all looks like that, in a sense where this bigger gap delta remain a constant, approach to some constant delta infinity. And then there's a small splitting below the gap, this epsilon approach to 0. So this kind of property is called a gapped property. Again, this is not a very rigorous definition, but it's more rigorous than looks like that. Okay, and I will come back to this point later to get even more rigorous definition. And then, so from here, these nearly degenerate states below this bigger gap, this delta is called the gap. Epsilon is not called the gap. Okay, and the state below this Hilbert space is called a ground state subspace. It's some kind of subspace in a total Hilbert space. And in physics, we usually call the gap states. The gap states in physics usually refer to this ground state subspace. So that's a more precise meaning of gap states. Really means it's a ground state subspace. Okay, so this is a gap system and a gap states. Okay, so let's give some example. So in the first example, it's a 1 + 1D system. Okay, and here I want to, again, there's some notation. When I say 1D, the small d, I mean the space dimension is one-dimensional. But in field theory or in string theory, people usually refer to space-time dimension. And in mathematics, people mostly refer to space-time dimension. So we use a capital D or 1 + 1D refer to space-time dimension. So 1 little d or 1 + 1 big D, it means the same thing. It's both refer to one-dimensional spatial system or 1 + 1D space-time system. Okay, and so if our graph is like that, and so the neighboring is have this definition, and then that's a 1D system, and on each vertex, we have a 2-dimensional vector space spanned by 2 basis vector we call spin up and spin down. Okay, so total vector space is a tensor product of a 2-dimensional vector space on all the sides. And the Hamiltonian is very simple. It's sum of Z operator acting on each vertex. Z operator when acting on spin up is a spin up. Acting on spin down is a minus spin down. So that's action of a Z operator. And from here, we can see, because the minus sign here, we see that lowest eigenvalue, or we call ground states, means all spin up. So the Z equal to 1. So the H is maximally negative. And so there's a unique ground states. It's every side is spin up. So every side spin up can be viewed as a tensor product of a spin up on each side, n times tensor product. And this tensor product states is called the product states. Again, it's a very important concept. And this product states is what we call trivial states. So trivial gap states means product states. Again, that's another concept we will use very often. Trivial means product states. And so another example we call the Ising model, where the vector space is same. So we have a 2-dimensional vector space per site, but the Hamiltonian is different. Hamiltonian is a sum of operator which act on the neighboring sites, Zi and Zi plus 1. So I just label different sites. Okay. In this case, you can see that this operator prefer the spin to be the parallel, either both up or both down. So their product will be +1 and it's more negative. And in this case, the ground state subspace is two-dimensional, either all up or down. So they all have the same degenerate energy, degenerate eigenvalue. And so in this, in the second example, the Hamiltonian, this Hn have a Z2 onsite symmetry. So where it's generated by this X operator acting on each side. So X operator is flipping the spin. Oh, there's no minus sign here. Sorry, there's a typo. And then we can see that the Hamiltonian, when the both Z get a changing sign, this product don't change sign. So Hamiltonian remain the same. Okay. So so Hamiltonian now have a symmetry. Okay. And for this, for the Hamiltonian have a symmetry. This is a symmetry of Hamiltonian. And then we have a notion of a symmetry breaking states. So what is a symmetry breaking states? So we know that this ground state subspace is two-dimensional. It can be spanned by so-called symmetric basis. We can say O up plus O down is one basis. O up minus O down is another basis. And these two basis vectors are symmetric, means that when the U act on this basis vector, we only get back, but up to the side, up to the face, we get those state back. So that's a symmetric, means action of a symmetry operator is equal to the invariant up to the face, really means invariant up to the face. Okay. But however, this symmetric basis is not product states. And we can choose another basis, which is O up is one basis, O down is another basis. Those bases are product states. But this product state basis is not symmetric. Okay. So this is so this tension between choosing this symmetric basis, which is not product states. A product state is not symmetric. And this kind of property is called a symmetry breaking. So symmetry breaking means we cannot choose symmetric product states as a basis of a ground state subspace. That's a symmetry breaking, which is another very important concept in physics. Okay. So now let's define the notion of a phase of a matter. Okay. So that's another concept. So there's a lot of definition here. And what is a phase of a matter? Because like in our first example, we have a trivial state, trivial gap states. And the trivial gap states is described by a particular Hamiltonian. This is a very, very particular Hamiltonian. Okay, very special Hamiltonian.
Sorry, what are the actual values of the gaps in these examples?
Actual gap example actually is 2, because if you flip a single spin, the Z from -1, +1 to -1, so changing by 2. So the gap is 2. And so in this example, this delta equal to 2. Epsilon is not defined because there's only one state below the delta. Yeah, so gap is 2. And the phase of matter is following. We can perturb this Hamiltonian. When you perturb the Hamiltonian, the spectrum still looks like that. But the eigenvector may be changed, but the spectrum still more or less like that. And the physical property is still more or less similar. So that's a motivation to define phase matter. It means the states are Hamiltonian which are similar. So what do we mean by really similar? Similar really means the following. For gap system, similarity are easy to define. For gapless, it's much harder. For gap system means we have 2 sequences of Hamiltonian. Each Hamiltonian have this kind of spectrum. Then as n go to infinity, they all have this spectrum. Now we can consider the deformation. We can deform one sequence of Hamiltonian into another so that this spectrum remain unchanged, remain to have the delta is approach to finite, and some constant and epsilon approach to 0, this property remain unchanged. So in this case, we say these two sequences are equivalent. Again, the definition here is not very rigorous, but you can imagine, I don't give a very rigorous definition, but just give some idea. So as n go to infinity, these two sequence Hamiltonian can deform into each other, maintaining this this kind of a gap spectrum. And then we say these two sequence Hamiltonian are equivalent. And then the equivalent class of this gap system or sequence Hamiltonian are called gapped phase of matter. Again, this is a concept used very commonly in physics, but by physicists, but the rigorous definition probably still not there. So so this is a gap system without symmetry, and we can also have a gap system with a symmetry. So symmetric gapped system. So what do you mean by the gapped quantum phase with the symmetry? So when you add symmetry, then it's very easy. The Hamiltonian would have a symmetry, means invariant under certain symmetry action operator. And then if the deformation path also have all the symmetry. So if two Hamiltonian can deform into each other via the path which maintain the symmetry, then we say that equivalent class define the gap system with the symmetry. Okay. So for the trivial gapped phase, and then the Hamiltonian, the ground state of Hamiltonian in this equivalent class. Okay, let me just say. So here we define the trivial states. This particular Hamiltonian trivial states. Okay, then it's a representative of a certain equivalent class. That equivalent class containing this Hamiltonian is called a trivial phase. Okay, so the ground states, this ground state subspace of the Hamiltonian in the trivial phase is called a short-range entangled because the following. Because this ground state in the trivial phase it's similar to product state because their Hamiltonian can deform into each other. It's similar to product state, but not exactly the same. But what it means by similar? So what's the meaning of similar? The similar really means the new ground states in a trivial phase is correspond to product states up to some kind of similarity transformation. This similarity transformation called the local unitary transformation. Okay, again, that's a very important concept, so we'll explain a little bit more. So each box here means a unitary operator, but they may act on several vertex. So in this case, this box have four legs, means they act on the 4 vertex, like 4 sides. And so it's a scrambled entanglement among these 4 neighboring sites. Okay, these 4 neighboring sites. And then we have another box, another unitary operator act on 4 other sites, and etc. So we have 1 layer. So certainly, this unitary operator only mixed up nearest neighboring sites. So only change the local property. So globally, still like a product states. So this naturally is a similarity. So that's what we call the local short-range entanglement. And certainly, we may have many layers for local unit transformation. They may not line up like that. So if a number of layers is finite, then the equivalence relation defined by this kind of local unitary transformation will correspond to this equivalence relation using gapped Hamiltonian. Again, it's no proof of maybe for some special case there is a proof, but in general we don't have proof of that. But the people believe that. So therefore, we can also use an equivalent class defined by local unitary transformation on the ground state or ground state subspace to define the gapped phase of matter. So physics is mostly using this definition. Okay, so that's really define the gapped phase. But our definition is not very rigorous. And so actually, in terms of local unitary transformation, our definition looks like that. Let me explain what this means. Remember, the gapped quantum system are defined by sequence Hamiltonian. And this local unit transformation really relate the ground state subspace for each size of a system. So N1 size. So this psi and psi prime are related for N1 for N1 site. For N2 site, they are related. They all related by local unitary. So this is what we mean by this relation. But this relation only for each fixed number of sites. And then we take a limit of n go to infinity. Then immediately we see that this is not proper because the system with different sites are not related, and they can be arbitrary. So this cannot be a right definition. This is obviously wrong definition. But we do publish paper using wrong definition. And so to make a better definition, to make a more correct definition, it's very important to relate a system with different sites. Actually, this idea is very much like a stabilization of fiber bundle. You can tensor product a trivial bundle to stabilize a fiber bundle. This is the same idea. So we define additional equivalent relation. That means if two ground state subspace, they differ by tensor product of product states, really like trivial bundle, then we say they are equivalent. So we build this equivalence relation. And once we build this relation, then this whole thing are connected. So this is a more accurate, more precise definition of a gapped quantum phase. But actually, to be more precise, this definition defines so-called a gapped quantum liquid phase. This connection with different size for arbitrary fiber of trivial states define this liquidness. So it means that these trivial states may not be uniformly distributed, can be randomly distributed. And that will define the liquid nature of a gapped phase. It's a very important, again, another important concept, because there's non-liquid phase, which I will not discuss. So the trivial phase and the symmetry breaking phase belong to this gapped liquid phase. So this is basically the topic we are going to study. So in this 3 lecture, we are going to study this kind of gapped quantum liquid phase, which is equivalent class of a many-body system. So how to classify them, how to understand them, what their property, and etc. So now you can see clearly that the definition here used is a microscopic definition in terms of lattice model, not in terms of topological environment, not in terms of measurable quantity, not in terms of experiments. So this we have this microscopic definition. So in the rest of this lecture, we'll try to come up with a macroscopic definition, how to using macroscopic or experimental measurable quantity to define this gapped quantum liquid phase, or to distinguish gapped quantum liquid phase, how to use experiments. The answer for that, actually, as I mentioned, is a higher category theory. Okay, so here I just want to make a remark that actually we defined the symmetry breaking states, okay, before, and here I want to define symmetry breaking phase, and because we have defined the quantum phase. So what is symmetry breaking phase? Usually in textbook, in physics textbook, people define symmetry breaking phase using some classical picture. And here I want to describe a quantum definition. So it means a symmetry breaking phase have degenerate ground state subspace. So the ground state subspace may be degenerate. And it have a short range correlated basis. Okay. So we can choose a basis vector which are short range correlated. That means that they are local unitary equivalent to a product states. Okay. And then, But once you choose these bases, very often you find the basis is not symmetric under the symmetry action anymore. So here our symmetry action are really described by a group GH, whose representation of this whose representation which leave this H invariant. So this is called symmetry of Hamiltonian. So this local entanglement basis is not symmetric, but however they are only symmetric under a subgroup. So therefore, this locally entangled basis, a short-range entangled basis, define a subgroup. This could be trivial subgroup. That means symmetry is completely broken, or can be smaller subgroup, means the symmetry is partially broken. So this G per psi is a symmetry transformation which leave the basis, this short-range entangled basis, unchanged. And so this really define symmetry breaking. And for the long time, and physicists think maybe this symmetry breaking phases is all the possible equivalent class of a gapped system. So so in this case, this symmetry breaking phase classified the pair of group, as I mentioned, a symmetry group of Hamiltonian and a symmetry group of this ground state basis, or this short-range entangled basis. And so in this case, the group theory became a mathematical framework for this kind of symmetry breaking theory, and people use that to classify this, for example, the 230 crystal in 3 dimensions using group theory. But however, it's clear that if you're using this definition very carefully, and it's pretty, maybe it's obvious that this kind of a symmetry breaking phase, probably is not do not capture all possible equivalent class. Experimentally, physicists realized that in 1980s, and via the quantum Hall states. There, people studied this 2-dimensional electron gas on the surface semiconductor in a strong magnetic field. They find that there's a Hall conductance is very, very accurately quantized in terms of rational number times the fundamental constant. So this is called a different Hall plateau. The different quantum Hall states correspond to different rational number should represent the different phase of a matter, quantum phase of matter. But however, this system have a dirts, have all the impurities, we still have a precisely quantized plateau. Actually, the dirtier system have a better quantization, have a better accuracy of the rational number. Okay. So for those dirty systems, the Hamiltonian have a no symmetry, and certainly there's no symmetry breaking. So there's no way to use symmetry breaking to characterize different plateaus. So that's led to the realization that there's a new kind of order, which is called the topological order, and which is beyond the symmetry. So there's a new equivalent class of gapped system, which is beyond the symmetry breaking. So so what is those new system beyond symmetry breaking? Okay, so the difficulty is really that for the many-body quantum system, it's described by a wave function of many variables, because the number of particle or number of sites can be 10 to the 20. And so the complex wave function, which is a coefficient of the expansion of this product basis. And this is just a very high dimensional vector space. And so basically it's roughly 2 to the 10 to the 20. So that's how big of the vector space is. So how to visualize, how to have intuition about this wave function, this complicated wave function, how to extract the topological invariance from this very complicated wave function. So that is a challenge. So the first proposal is that we put this system on the space with a various topology. For example, for two-dimensional system, we can put this wave function on the sphere, on the torus, Riemann surface, and etc. And then we measure ground state degeneracy. It turns out that on different spatial topology, the ground state degeneracy can be different. So this different ground state degeneracy play a role of topological invariance, which can distinguish different class of this many-body wave function. So that is a idea. But there's a problem here because the ground state degeneracy, especially without symmetry, you see there's no degeneracy because for generic Hamiltonian, generic Hermitian operator, the spectrum is not degenerate. There's always splits. So what do you mean by the degeneracy? So actually the degeneracy means that as the system size go to infinity, this degeneracy is getting better and better. In particular, as the system size go to infinity, this degeneracy do not depend on the local perturbation. So even when you add the perturbation, you add the dirts to the Hamiltonian, you still split degeneracy. But as the system size go to infinity, the splitting gets smaller, regardless what kind of perturbation you put in. So there is some kind of robustness. Actually, it's topological robustness because this degeneracy in large system size limit is robust against arbitrary perturbation. So actually, that's why we call this topological. Really, this topological robustness against arbitrary perturbation. So this degenerate have this very special property. So that's we call this a topological degeneracy. Let me say why we have this special property. We'll explain later. And this kind of topological degeneracy can only be changed if we have things like this level crossing. This represents the first order phase transition in physics. I will not go into that detail. Or via so-called second order phase transition where the energy gap is closing. So this is a non-degenerate ground state. This energy gap delta, and this other spectrum. But this gap delta may become zero and reopen again. Then the degeneracy may change. So this represents a second order or continuous phase transition. So in this sense, we say that the topological degeneracy is topological invariant describe different phase. They remain the same in the same phase. They can only change after phase transition. Okay, so that's so this topological degeneracy is used in this way in physics. Really try to define topological order. Okay, but however, this topological degeneracy just give you a single number in 2 dimensions for each genus Riemann surface. Okay, so they have a sequence of integer. And so you may ask whether this sequence integer for each genus provide enough information to label all possible topological order or all possible equivalent class of a gap system in 2 dimensions.
Sorry,
yes.
I don't see the relationship between the vector subspace of ground states and the genus G surfaces that you're drawing. The subspace is a linear subspace. So where is this topology coming from exactly?
The topology coming from this the degeneracy of the dimension of a subspace depend on this topology. So this D1 is dimension of this vector space. D2 is dimension of vector space, but for genus GC system.
And why have we associated a genus G surface with the dimension of the subspace?
Yeah, so this is a very, very good question, and I kind of glossed over. And so this really relates to this. That is because let me go further back. Because this Hamiltonian is defined so-called locally. You can see this Hamiltonian only see neighboring vertex. Okay, so you can imagine. So again, this not very rigorous, but you can imagine that we have a Hamiltonian defined on a sphere. If this is a triangulation of a sphere and a triangulation of torus, the local structure may be similar. So that's allow us to define a notion of so-called similar Hamiltonian, which is locally similar. I did not define that very rigorously, but we assume this can be defined. And then we have a sense of a system whose locally is similar, but globally have different topology. Yeah, you have very, very good question. This is something I'm trying to hide, but we must have this notion. And we assume we have this notion, this locally, we have a system which can locally define, but globally have still some ambiguity. And so we come to this. Actually, this question is so deep. Let me just spend some time on this. This local notion actually is really a sense of a manifold, because when I say sphere and a torus, we are talking about the manifold, which is locally similar, have tangent bundle and things like that. So this tangent bundle of manifold and neighborhood really corresponds to this local term in the Hamiltonian, which we say is similar. But when you do this on the graph locally are different. So we pretend they can be defined similar, even though the graph could be looks different on different places, like here and here. Graph is different, but we still say they are similar because they represent similar tangent bundle and things like that. This really regarded to the emergence of geometry, emergence of continuum from the lattice model, which is a very, very deep question. And why the geometry, why the notion of manifold should play a role here. And this is an open question, and we don't have a rigorous answer, but we have a belief. Then we say these things works, and we just go ahead. And but the rigorous definition, how the geometry, how can this manifold emerge from this lattice model, is highly non-trivial. And actually, the geometry for this quantum Hall states, the geometry emerge is not manifold. Actually, it's a framed manifold. So this framing structure is also a play role here. But those are subtleties. But those are very very important key questions, which I will not really address. But it's an open question, and hopefully the further development can come up with the answer. But this is a very, very important question. Okay, so with this in mind, so we have a sense of a similar quantum system locally but globally different, and this global difference gave rise to different Grancy subspace, and which in turn let me just clear this. And which in turn define this topological invariance. But however, this sequence integer do not provide enough information. Okay, and the sequence they do not provide enough information, and we want to have more information. Okay, so so how to obtain more information is the following. So let's consider let me try to do something. Okay, I keep opening the chat window. Okay, yeah. So so to obtain the more information, we can consider so-called vector bundle on moduli space. So we try to obtain a better, more complete topological invariance instead of a dimension for degenerate ground state subspace. So the idea is that we consider, again, because the questions make me easier to explain this. So we start with a manifold now. We consider closed two-dimensional manifold, which is a spatial manifold, okay, which has a metric. Again, the notion of a manifold, not notion for lattice Hamiltonian. Okay, and then we have a definition of moduli space, which is a diffeomorphism equivalent class of the matrix is some kind of moduli space of this manifold. Okay, and then we can triangulate this two-dimensional space to get a lattice or graph, and we can define so-called local Hamiltonian in terms of this metric. So now our lattice Hamiltonian would depend on the metric. So in this case, the space of a Hamiltonian really became the moduli space. Again, we have a jump. Again, this jump is what I just discussed. The going between discrete lattice to continuous manifold. Very deep things. Okay. And so now we can view the moduli space as a space of Hamiltonian, and actually space of a gapped Hamiltonian. Okay. And then the ground subspace for each point of moduli space will be the vector, because this vector space, ground subspace is a vector space, n-dimensional vector space. N is a dimension of this vector space, or degeneracy. Ground degeneracy is n is degeneracy. And so you can see that on every point of moduli space, we have a ground subspace, and all together we get a fiber bundle. We get a vector bundle on the moduli space. And this vector bundle would carry more information. And we wish, so rather than say this is conjecture, we can say this is the physicist's wish. We wish this vector bundle completely characterize the topological order. So we don't know if it's true or not, but if it is true, you can view this vector bundle as a definition of a topological order in 2 dimensions, or actually in higher dimension, maybe the similar thing is true. And so therefore, so this is really going from microscopic to macroscopic. And so we try to study the vector bundle in the moduli space of a manifold.
Can we understand this manifold is some sort of geometric realization of these lattice, or it's not at all?
Yeah, it is. So in a sense, this lattice model have no geometry, no manifold. But however, when n go to infinity limit in a very large graph, and the graph became very fine triangulation of something. And then there's an emergence. There's somehow the notion of a manifold, a notion of tangent space, or those geometrical notions somehow comes up. And I think this may relate to Anton's talk, because in large n limit, the topological continuum field theory comes out. And the topological continuum field theory actually defined on the manifold, not on the lattice. So somehow this manifold, this notion manifold come out. But however, this process is highly non-trivial, because actually here I say diffeomorphism equivalent class of a metric. Actually, this is wrong. For quantum Hall states, as I mentioned, this does not work. We have to add additional structure, in particular the framing structure. So more precisely, it's a framed manifold emerge from quantum Hall states. So this moduli space should be the moduli space of framed manifold, not just an ordinary manifold. So you can see different geometrical structure may emerge differently for different quantum systems have different geometrical structure. Again, this is a very interesting, promising direction, and we wish we can study more systematically. And but this is a question. Yeah, this is what we have now. So any additional questions?
So what's so what's special about 2D here?
Nothing. The 2 dimension is easier, and but in presumably this vector space, moduli space works in all dimension. Yeah. So
okay.
Nothing special about 2D.
Thanks.
Can you repeat the answer? Why 2 dimensions?
Oh, it's because a quantum Hall state is discovered first. That's 2 dimensional. So people study quantum Hall states a lot. So study 2-dimensional topological order a lot. And but for this conjecture, I don't know. Yeah, and I should say this really wishful thinking. And actually, I don't understand why it's so special for 2D. And in my mind, at the moment, at least, 2D is not special. And any dimension, it should be fine. And okay, let me say the caveat. Caveat is that it's possible, certainly this vector bundle in the modular space for arbitrary dimension, they are topological invariants, they are the data. What is unknown is that whether its data is complete or not. Here, the claim is that the data is a complete calculation of a topological order of equivalent class. This we don't know. And so actually, in the rest of the lecture, we are going to switch gears. We are going to add the punctures to the manifold. Means when adding punctures or adding these defect lines of defect membranes, it's like consider excitations. So in the rest of the lecture, we'll study excitations mostly. And so that's led to higher calculus theory. And here, certainly, so in that really means if this modular space is a modular space involving punctures, means both space topology and the puncture excitation, then that's more likely they are complete. Without puncture, whether they are complete or not is unknown. Yeah. So this conjecture basically say, without vector bundle modular space without puncture, whether that's already enough. This we don't know. Yeah. So this vector bundle is n-dimensional vector bundle. N is a ground state degeneracy on the spatial for certain spatial topology. Okay. And this vector bundle would have a curvature or have a monodromy. Okay. However, if the loop, if you consider contractible loop, if loop is contractible, then this monodromy turns out to be only U1, not a generic UN, because it's a UN bundle. So monodromy in general is UN. But here, for the contractible loop, it's only U1. Okay. And this, I won't explain that, but this really due to this notion of topological degeneracy. Because degeneracy is topological, and this fair bound is special. This local monodromy is only U1, so curvature only in the U1, not in UN. And this U1 bundle have a curvature, and this curvature are related to the so-called gravitational Chern-Simons term in the effective action. So this omega-3 is a gravitational Chern-Simons term. This is C is a coefficient of C is a chiral central charge for the edge states or some chiral central charge for some modular tensor category. And they are related to the quantization of thermal Hall conductance, which can be measured experimentally, which actually is measured recently, maybe 3 years ago by experiments. They measure the chiral central charge or the coefficient of a gravitational Chern-Simons term. And so that's one information. But the other information coming from this pi1 of a modular space is non-trivial. For example, the modular space, if the space is a torus, if space torus, it has a modular space. And that modular space is this, I don't recall, I think it's also called a modular space. And so this pi1 is SL2Z, is a modular transformation, and have two generators called S and T, which is Dane twist and the 90-degree rotation. And so therefore, this for the non-contractible loops given by pi1, we have the ICUN connection, and which is flat because locally the ICUN is flat. Only for non-contractible loop we have ICUN connection, and which define the representation of a modular group. This SL2N. So that are more precise project representation of this group. And so this ST matrix plus this central charge is more information. But that's more information can only come from a torus. On genus 2 Riemann surface, genus 3 Riemann surface, we have similar modular group for the high genus Riemann surface, a mapping class group on high genus Riemann surface, where more representation. And so maybe those data in 2 dimensions, those data may be enough. And we hope this maybe those data can characterize topological order. Okay, so so this basically is a macroscopic definition of a topology order. And I think time is up, and so it's a natural place for me to stop here.
Okay, great. So we can allow very short questions. And we'll make a 15 minutes break. Then David will give the second talk. Is there some short questions? Otherwise we sort of constrain the discussion, long discussion in the section. It's to be noticed, not the breakout rooms in Zoom, but it's another section. After 3 talks, then you will go. We will provide 4 parallel sections. I guess Xiaogang will go to the first one. Then we go to the second, then you can enter each room to discuss with a speaker.
Also, do you want to say there's a change of schedule from Wednesday to Friday?
Yeah, exactly. There is a change of schedule, which I just sent an email to everybody. So the original Wednesday section in the morning is now changed to Monday, sort of early afternoon, right? It's changed to Friday early afternoon from 1 p.m. To 3 p.m. And then so on Friday last day we'll have like 5 talks, and so upshot of the event. And yes, and so maybe the time is more suitable for everybody. Okay, if so, I actually will not end the section. It's like we just imagine we're in a big hall. You can leave or switch off camera, but I won't stop it. Okay, and at 16:15, David will come over, and I will come over a bit earlier to set up the slide with David. Okay, great. So see you.
Thank you.
Yeah, you're welcome.
I'll
Thank
sharing
you.
my screen.
Okay, let's see. Okay, so that's good. So we rest a little bit and come back. Okay. Hi, David. I made you into a co-host, and you should be able to share your slides, I think.
Yes, I will now share the slides.
I see.
I will also perhaps make sure that I'm the one that can annotate them. Okay. Ideally, it would be nice to set things up so that only the hosts can share the screen. In order to avoid Zoom bombing. I mean, I understand all the participants are registered, so it shouldn't be a big problem. But,
okay. I actually do not know how to do that technically. So yesterday we were still trying to record it, but somehow today it was possible to share. Maybe I asked the technical responsible person now how is that possible? Oh, wait a minute. You mean that? Oh yeah, no.
No, it's okay. It's not a big deal. I just.
Okay, so it's only me who is streaming on YouTube, not anybody else. Oh.
That was not my concern. Well, the same way as I'm sharing my screen, any participant, I believe at the moment, can share their own screen and overlap and override mine.
I think
allows for a range of malicious options, which
okay,
are best
really
prevented.
I think we excluded yesterday, so only the co-host can share the screen.
Very good, very good.
Yes, we excluded. And someone is asking you, can you also share the slide?
Sure. Just a second.
Yeah, great. Thank you.
Right. For what it's worth, I do not see a way to write over your screen right now.
Oh, because I deactivated it just now. I deactivated the annotation, but I don't think this sharing is I mean, at least during Xiaogan talk, I saw the share screen button on my screen.
Yes, and I see a button that says, this will stop others screen sharing. Do you want to continue?
That's right. So ideally that would not be there in an ideal world.
But the problem is with Zoom is that I think this is something that either Chen Cheng or somebody at ESI has to fix inside the settings.
Yeah,
that's I'm not sure it can be set. I'm not sure it can be done after the fact. It's probably something that's set up at the very beginning of the.
Right. So we raised this issue yesterday, and we well, I think.
I know I can do it. I can just do it. It's in the security tab. So I will now not allow participants to share the screen. I will allow them to chat and not annotate. Okay, very good.
Okay.
So if you click the security tab, at least I see it now that I'm sharing. I see the great tab on top with mute, start video, security, participants, and so on. I think the host has a security tab which allows these things to be.
Oh, okay. I see. Okay, so yesterday, the Zoom master told me that he will set this up, but okay, it's actually me. I should do it. Okay, thank you very much.
Anyway, I've done it now because I'm co-host. So.
Okay.
Very good. Do I start now? Do I?
Yes, yes, please. Thank you.
I have 45 minutes. Is that correct?
Yeah. Yes, exactly.
Also,
but
maybe
you start late, so you can.
Sorry, let me turn on my video too.
Thank you.
Okay, very good. Okay, so I would like to discuss topological aspects of quantum field theory. Several of the topics that I will discuss appeared in projects with Theo Johnson-Freyd and my student Justin Culp. Sorry. Okay. So most of what will be discussed in this conference concerns topological quantum field theory and its applications to in mathematics and condensed matter, and so on. Now, topological quantum field theory is a very special type of quantum field theory, which, and if I was an old-style particle physicist, I would consider a completely trivial quantum field theory because it has no local dynamics. Topological quantum field theory has no excitations, there is nothing to scatter, there are no local operators to compute correlation functions of. And as Professor Wen was discussing, the only way to get non-trivial information in topological quantum field theory, the only observables you have available are global. You need to think about partition functions or space of states on space-times of non-trivial topology. Or perhaps you need to look at defects, something called topological defects, something like anyons, which represent sort of UV excitations, which are so massive that you cannot create, but if somebody gives them to you, you can move them around and probe their properties. And so a lot of these categorical tools that are developed in mathematics to study topological quantum field theory capture the properties of these categories of topological defects. Now, if you're studying a general quantum field theory, though, you have local dynamics. You have local excitations, there will be a scattering matrix, there will be local operators you compute correlation functions of. Still, it's hard to imagine that all this interesting global stuff that we've been studying for topological field theory will just disappear. So on top of these local excitations, local data, there must still be some interesting layer of global data, of topological data. And so the sort of questions I would like to ask in this talk concern the topological or global information which is needed to fully characterize the quantum field theory on top of the local data. In particular, I'm curious to understand if the tools that we already have to study topological phases are enough to characterize these properties of general quantum field theories or not. So as an appetizer, let me just try to convince you that there is indeed interesting topological subtleties, even in the study of very basic quantum field theories. Now, of course, I should say immediately, right? If I have a quantum field theory, I can always stack it with some topological quantum field theory, some extra topological phase. This will add some interesting, this will change partition functions, correlation functions, will add topological details, but which do not talk at all with the original degrees of freedom. So that's a bit boring. I would like to discuss a situation where you can add or modify the topological aspects of the theory in a way that couples in an interesting way with the local dynamics. So let's think, for example, about the 3D Ising model. This is a nice quantum field theory, a conformal field theory actually, which describes the second order phase transition between a system with unbroken Z2 symmetry and a system with spontaneously broken Z2 symmetry in 3 dimensions, in 2 + 1 dimensions. This is the simplest CFT with Z2 symmetry. It has one relevant operator which preserves the Z2 symmetry, and one relevant operator, the spin operator, which is odd under the Z2 symmetry. If you deform the theory by this Z2 even relevant operator, you get a whole RG flow, actually 2 depending on the sign, which sort of describes the high temperature or low temperature phases of the Ising model. And so you get RG flows that go to the spontaneously broken phase or to the trivial phase. Now, what can I do to this theory which would leave the same, which leave the local dynamics unchanged, but change the global topology? Well, the simplest thing I can do is to gauge the Z2 symmetry. So Z2 gauge fields have no local dynamics. So adding Z2 gauge fields to the system will not change the local dynamics. It will change correlation functions. It will change topological properties of the theory. I'll get a new theory. How does this theory look like? Well, one basic difference is that it does not have the original Z2 symmetry anymore because it has been gauged. It has new topological defects because the Wilson lines for this Z2 gauge theory are topological. They can be deformed freely. If you know about high-form symmetries, these Wilson lines generate a new dual Z2 one-form symmetry, global symmetry. Okay, so we got one new quantum field theory, which locally is indistinguishable from the 3D Ising model, but is still different globally. We can do something more complicated. We can take the 3D Ising model, stack it with some topological order, with some topological quantum field theory with non-anomalous global Z2 symmetry. For example, we could stack with the toric code, which has a Z2 symmetry which exchanges E and M quasi-anions, quasi-particles. And then we can gauge the diagonal Z2 symmetry of the combined system. This gives me some bizarre quantum field theory, which shares a lot of local operators with the 3D Ising model. It has some fancy collection of topological defects. For example, it still has the topological Wilson lines, but now it will have extra topological anions that look like E plus M or F, if you know the name of anions of the toric code. So you can see that just starting from something very simple, which is a quantum field theory with a Z2 global symmetry, I can build a huge family of quantum field theories which are related to it by some topological manipulation. The topological manipulations I described here, where I stack with a topological field theory with Z2 symmetry and I gauge the diagonal, provide me a very large class of examples. I think it's reasonable to conjecture these are essentially the only things I can do, pretty much because the Z2 global symmetry is the only topological. Well, okay, I can try to give some arguments for that later, but especially the idea is that the 3D Ising model does not have other topological defects except for the domain walls which implement the Z2 symmetry. So the domain walls across which the spin flips. So one could conjecture that this sort of procedure exhausts all the topological variants of the 3D Ising model. And so in this case, the topological variations of the 3D Ising model will be classified by a problem which can be treated using the standard technology of topological field theory. Classify topological field theories with a non-anomalous Z2 symmetry. But even if I can imagine a situation where I've been given not the 3D Ising model in its simplest form, but I've been given one of these complicated relatives, which have a large collection of topological defects, topological anions, and so forth. It's not quite clear to me how would I have recognized that that complicated theory was just some extra topological layers coupled to the 3D to a simpler theory with Z2 symmetry. So one possible question you can ask is, if I'm given a 3D theory with a certain collection of topological defects, how do I figure out if this was perhaps just a theory with Z2 symmetry in disguise? Now, just to give another example to show that sometimes the local and the global are completely separated, you can just take the 3D Ising model and deform it by the spin operator. This breaks the Z2 global symmetry. It gives you a quantum field theory which has just no symmetries, and as far as I know, has no topological defects at all. And so I would expect that a theory like that cannot be coupled to extra topological degrees of freedom in any interesting way. So in that case, I would get a theory which has no topological variants except for stacking with some topological field theory. So, right, so we want to have this notion of quantum field theories which are topological relatives, which have the same local dynamics, but different global properties. Now, I will not try to be specific on what do I mean with local dynamics. Intuitively, it should be really something like, what's the collection of excitations I have in their scattering matrices? Or perhaps, what's the collection of local operators I have in their OPE, operator product expansion? For the mathematically oriented part of the audience, perhaps I could think that the local dynamics are described by some factorization algebra of local operators. And the extra global data is something which generalizes factorization homology, some extra information I need to build correlation functions which satisfy both word identities, but also are globally well-defined. Let me just give you another quick example of topological relatives, which you're surely familiar with in a different language. Take the 3D model at high temperature, the 2D model at low temperature, or the 2D free fermion. And these are three different quantum field theories. They have different correlation functions. Nevertheless, they have the same local dynamics. There are these transformations called Kramer-Vanier duality or Jordan-Wigner transformation, which relate these two theories up to small global issues. And they're really just different. They're just sort of celebrated names for simple operations like gauging a discrete Z2 symmetry. So, right, so as Sagan was mentioning, in the case of topological systems, we expect the differences between topological relatives to emerge when you look at spacetimes on non-trivial topology, or when you look perhaps at the topological defects of your theory. Let me give another example which I encountered several times in the past. Let's take a four-dimensional SU2 gauge theory, Yang-Mills, and compare it with a four-dimensional SO3 gauge theory. No matter, just gauge fields. So these theories have the same gauge Lie algebra. The connection really looks the same. The gauge field looks the same. You can build the same local operators out of them. So these theories are really the same local operators. Still, they have different partition functions on the manifold non-trivial topology, because in the path integral, you have to include either non-trivial SU2 bundles or non-trivial SO3 bundles, and these are different notions. Now, if you look at the problem a bit more carefully, you realize that these two theories also differ by gauging some discrete symmetry, although it's a somewhat more exotic form of symmetry called a one-form symmetry. And again, you can ask, what's the space of all possible variations of this four-dimensional SU2 gauge theory? And this is a question which in high-energy physics or string theory or supersymmetric quantum field theory does occur in interesting ways. For example, there are dualities which relate different quantum field theories, but often if you look at it carefully, they relate fancy topological variants of different quantum field theories. Are there any questions?
Someone has a question. Yeah, please,
Okay.
sorry.
Oh, can I ask a question?
Yes.
Is the example of in the rational conformal field theory saying they might have the same VOA, but
oh, absolutely.
They will have. Would that be the example of your?
Yes, absolutely. I'm going to give a few more examples momentarily, and that will be the first. One of the important ones. So definitely, a lot of these considerations were originally found in two-dimensional conformal field theory, where people started encountering things like different modular invariants for the same rational conformal field theory. Okay.
If I may,
I
raise my hand.
Yes, go ahead.
So would you consider a theory and an overflow of this theory in 2 dimensions the same or not the same?
I would say they're different theories with the same local dynamics.
But the set of local operators is different.
Sometimes it's different, sometimes it's the same.
No, but so consider an overfold that has a twist field.
Oh yeah, no,
Local
absolutely.
dynamics is different.
Yes, I would like to have a large set of local operators closed under OP. I'm okay if some theory has a few. I mean, the spin operators in the case of the Z2. So right, so Nati was referring to the fact that if I look at the 3D Ising model, after I gauge the Z2 symmetry, the spin operator is not there anymore because it's odd under the symmetry. It's not there as a local operator. It still exists as something that lives at the end of a topological Whiston line. So you can still consider correlation functions of these spin operators. It's just that they carry, they have a topological tail. And so if you look at if you start moving your operators around, you might find multi-valuedness. But the local dynamics is still the same.
My question was actually about the two-dimensional case, where the local, so if you take, say, a circle and a Z2 overfold over the circle, would you consider them the same or not the same?
I would consider them
now
different.
We have a local twist field. Now there's a local twist field. It's a local operator that is different.
Yeah, I would consider them different quantum field theories with the same local dynamics.
But the local dynamics is not the same because you can have the twist. You can deform the action with a twist field.
Well, then you change the theory. So absolutely, if you allow yourself, so this notion is not robust under deformations. Absolutely. As I was saying, the 3D Ising model deformed by a magnetic field.
No, I think 3D is too complicated because the twist field is a line. I'm talking about
No, just deformed by the spin operator. They take the 3D Ising model, deformed by the spin operator. This breaks the Z2 symmetry, so it kills the relationship to a Z2 gauged 3D Ising model. So it's perfectly true that two topological relatives could have different choices of local deformations available to you. And some of those can break the relationship.
So you would say that two theories that in two dimensions that differ by gauging, i.e. overfolding, are topological relatives.
Yes.
Okay.
Now, there are
this is not the standard definition.
Well, I never know what the standard definition is because there is no textbook on quantum field theory that treats these issues properly. So I don't know what the standard is. We are still waiting for somebody to write a good textbook that fixes the standard. But I have to say already that in two dimensions there are all sort of issues that make my definition a little bit iffy. For example, you could say, okay, I'm happy with just having the stress tensor and everything obtained from OP of the stress tensor with itself. Well, then you would get to sort of put in relationship theories which just have the same central charge but share very little else. And I would not feel comfortable calling those topological relatives.
Okay.
So I see problems with my definition already.
Well, it's the same problem as with the overfold.
Well, the orbifold, it's not as, for the orbifold case, it's really, the two theories are obviously related by topological manipulation because they're related by adding a Z2 gauge field, which does not change local dynamics because it has no dynamics.
But you had a conjecture that the set of deformation, the manipulation that you said exhausts everything. So you can't use that as the definition of your set. I really don't want to derail your talk, so
no, it's fine.
I'm going to mute my microphone now.
This is a talk which consists mostly of questions on my part, so I'm happy to discuss. But okay, I'll keep going, and then we can discuss more. I hope we can discuss more.
So, can I do one follow up on Nati's questions?
Sure.
So is the sort of, I don't want to try to make this precise, but is the idea you're trying to get at that somehow the two systems have like a common sub thing of finite index, with finiteness being an important part there?
Yes, something like that. And then I get in trouble because sometimes I can have a collection of theories, each of which is related in some finite way, but not all together.
Oh, okay.
Not all related in a finite way at the same time.
Wild. Okay, thanks.
Oh, no, it's not that wild. I mean, just take a theory which is a U1 global symmetry. I can gauge a Z2 subgroup. I can gauge a Z3 subgroup. I can gauge a Z4 subgroup. I can gauge a Z5 subgroup in a topological way without changing local dynamics. But I cannot gauge the U1.
Okay, but any finitely many theories you just produced are related by a finite index.
Yeah, they are all related to each other in a finite way, but not at the same time.
Well, that's because you had an infinite, you have too many. You have to get your order. Anyway, you should continue your talk.
So
but
my problem is that in a quantum field theory, which is not topological, I can have categories of topological defects which are too large to be treated with the standard methods that are employed in topological quantum field theory. I'm not saying that they're very different, but there is at least a possibility that some tools are needed which are not needed in the topological case. Okay.
So someone else also have a question, or is that short? Yeah, maybe David should just go
I have
ahead.
another question session later. Okay, so right, so when we relate this gauging a discrete symmetry, it's one example of a topological manipulation. So which topological manipulations have we encountered now? We can start with the topological field theory. We can gauge a discrete global symmetry. Perhaps it's an n-form symmetry, perhaps some kind of generalized symmetry. And towards the end of the talk, I will discuss an interesting generalization of the notion of gauging a symmetry, which is a condensation. In all of these manipulations, the crucial ingredient seems to be the category of topological defects of your theory. I should stress that even if your quantum field theory is not topological, the topological defects still form a category. So a topological defect is, by definition, a defect of some conformation which can be deformed freely. In order to make a sharp definition, I would really need to define for you what a defect is, and I will try to avoid that. But just imagine a modification of the theory, which is local in some normal direction. And it's topological if you can give it whatever shape you want. A small changes of shape don't change the answer. So a Wilson line in the topological gauge theory is a good example. In a discrete gauge theory is a good example. For interfaces, the notion of being topological is essentially that you are transparent to the stress tensor. You can pull it across, you can bring the stress tensor as can be brought to the defect from the left and from the right to the same answer. But for defects of higher dimension, it's a bit more complicated. In any case, it's collection of defects, and actually the collection of, I should say better, the collection of topological relative quantum field theories form a higher category. Because whose objects are the theories, the morphisms are the topological interfaces between theories. The morphisms between morphisms are, interfaces between interfaces, and so on and so forth. And one of the mathematical questions is what axioms does the higher category of topological relatives of a quantum field theory satisfy? So there is a good axiomatization for the category of topological field theories in some dimension. I would like to see a similar axiomatization of the category of topological relatives of a given quantum field theory. And as I was discussing with you, I expect that some finiteness constraints of dualizability might be modified in principle. And in a sense, this is a categorical version of the notion of factorization homology. Now, in a lot of situations, although not all of them, there is a very nice construction which separates in a neat way the local and the global problem. Separates the dynamics from the topology. So this is possible when you can take your original theory, which I call T here. I think you can see my mouse, is that correct?
Yes.
Yes. And you blow it up to a sandwich, to a slab in in one dimension higher, where you have some topological system in one dimension higher. You have a dynamical boundary condition where all the local dynamics of T lives. And you have a topological boundary condition where all the topology of T lives, all the topological defects and so on. If you can do that, then also topological manipulations applied to T will essentially only modify the boundary, the topological boundary. And so the topological relatives of T, you would expect to look like other segment compactifications, where you keep the same dynamical boundary and you change the topological boundary. And the theory that lives in the bulk is presumably something you can reconstruct from the property of the topological boundary. It's some generalization of the center or whatever lives at the topological boundary. So if you have a construction like this, then you can use standard technology. All the topological relatives are going to be described by possible gap boundary conditions for this particular topological bulk. And I should mention that you can really push all sorts of topological information to the boundary in favorable situations. For example, even notion like, is this theory bosonic or fermionic? Well, you can typically, even if the theory is fermionic, you can usually find a setup where the dynamical boundary is bosonic, the bulk is bosonic, and only the topological boundary knows if you have fermions or not. So it sort of simplifies the problem to classifying fermionic or bosonic boundary condition, topological boundary conditions for some topological bulk. Let me give some examples. If I go back to the case of discrete symmetry, like the 3D Ising model, what you can do is you can take the 3D Ising model and couple it to a 4-dimensional Z2 gauge theory. And then you can put, every discrete gauge theory has a canonical boundary condition called Dirichlet boundary condition, which sort of kills the gauge group, makes it the global group, symmetry group again, fixes the connections to some value. And if you take your original theory, you couple it to a 4-dimensional gauge theory, and then you put the Dirichlet boundary condition on the other side, you just recover the original theory. So in this setup, sort of the bulk is simply a G gauge theory with an action which is just whatever anomaly my original theory had. So it's a Dagger-Witten theory. And then you can think about what are the possible boundary topological boundary conditions for a Dagger-Witten theory. And actually, the fact that Dirichlet boundary conditions sort of give you a bijection between theories with G symmetry and boundary conditions of a G gauge theory can be applied both to the dynamical boundary and to the topological boundary. And so here you can sort of convince yourself that all sort of topological boundary conditions come from coupling the G gauge theory to some topological system with G symmetry. So this is sort of the maximally clear situation. And there are easy generalization to fermionic situations where your symmetry group includes -1 to the fermion, includes -1 to the fermion number. You might have to use some sort of a spin gauge theory, which is a gauge theory where the gauge field is actually a spin connection. But again, everything works in a reasonable way. If you particularly, just to give a particularly simple example, if you go back to the problem of the 2D Ising model versus free fermions and the Jordan-Wigner transformation or Kramer-Vanier duality, well, all of those can be understood in terms of properties of a 3D Z2 gauge theory. The 3D Z2 gauge theory has sort of 3 boundary conditions which are related by Kramer-Vanier duality or Jordan-Wigner transformations. 2 of them are bosonic and 1 is fermionic. Anyway, I think, I'm pretty I have negative time already, right? So I better move on fast. You can do a similar construction for the 4D gauge theory example. You use a 5D.
That's not true. You began at 16, 17, right? Isn't it? You can continue until 5
Oh, I can't. Sorry, because on the schedule I had 45. Ah, no, 45 minutes. Yes,
45. Therefore, yeah.
Okay. Good. Okay. Anyway, so right, so you can build a setup like this rather easily in every situation where the topological manipulations are involved in some discrete symmetry, just by using in the bulk a gauge symmetry, discrete gauge symmetry in the one-dimensional hierarchy.
Excuse me.
Mm-hmm.
What is the exception? What is the example in your mind that this does not work?
Well, as I mentioned, if I have a U1 global symmetry, then I cannot gauge it in a topological way.
Okay.
So I cannot describe all topological variants as boundary conditions of the same bulk. Another example occurs in rational in two-dimensional quantum field theory. So it's very well known that if you have some rational conformal field theory with some chiral algebra A, then you can describe, it can always be described as a sort of topological sandwich in 3 dimensions, where you have the chiral algebra lives on a boundary, and on the other boundary there is a choice of modular invariant, which is a boundary condition for the quantum double of the category of modules of the chiral algebra. But it's perfectly possible to think about situations where this breaks down. For example, if you take just the simplest holomorphic theory, the E8 at level 1 rational conformal field theory, it's very easy to define topological defects which preserve only a subalgebra of the chiral algebra. And there are really a lot of them, because you can pick very many different rational subalgebras of this chiral algebra, and they're not all, I think there are definitely too many to fit in a fusion category. And so there is no way to describe them all in this sort of language where I have a quantum double in the bulk and a fusion, a Turai zero in the bulk and a fusion category at the boundary.
Thank you.
So in general, when these things can be done, they're very useful, but it's not obvious to me that they can always be done. And I would like to understand better what is the correct language to treat all topological manipulations at the same time. Let me give a nice example of possible applications of these sort of constructions. So suppose you want to study the RG flow of your theory. Now, I'm assuming an RG flow which does not break the topological data that you're using to relate different theories. Then, because all these theories are the same local dynamics, you expect the RG flow to also be related. And indeed, topological manipulations commute with RG flow. So if I go back to the 3D Ising model, we know that this 3D Ising model has 2 deformations. It preserves the 2. One lands on the trivial phase and one lands in the spontaneously breaking phase. And that's why we say that the 3D Ising model is the natural second-order phase transition between the trivial phase and the symmetry breaking phase. Now, suppose I do some topological manipulation of the system. This operation commutes with RG flow because it's topological. So, for example, suppose I gauge the Z2 symmetry of the 3D Ising model. On one side of the RG flow, I'll obtain the Z2 gauge theory coupled to the trivial theory. So I get the toric code. On the other side, I will find a symmetry breaking phase, and I'll gauge the Z2 in a symmetry breaking phase, but that gives me the trivial phase. So a way to think about this Z2 gauged 3D Ising model is some theory that lives between, as a second order phase transition between the toric code and the trivial theory. Suppose I look at a more complicated manipulation like this, where I stack the 3D Ising model with some TFT and then gauge Z2. Well, if my RG flow landed on a trivial theory, then I'm obtaining the Z2 gauge version of the TFT I'd stacked. If my RG flow lands on the Z2 broken phase, well, that sort of undoes the Z2 gauging. So this fancy modification of the 3D Ising model is a natural candidate for a second-order phase transition between the topological order with Z2 symmetry and the topological order obtained by gauging the Z2 symmetry. So any sort of RG flow for a basic theory gives me a collection of RG flow statements for the topological relatives. And so that's one reason we might want to look at topological relatives, because they're an RG flow invariant notion. So if you have a picture like this, and you have to RG flow, say to a gap system, then your dynamic boundary, the RG flow can only touch the dynamic boundary condition, because that's the only thing that has dynamics. It will not touch the bulk, it will not touch the topological boundary. So the endpoint of the RG flow must be described as some infrared boundary condition, possibly gapped, sandwiched with whatever topological boundary condition we had before. And so we get some formula, right? That the infrared dynamics of the infrared phase of T is the result of sandwiching the infrared brane with B. The infrared of T prime is the result of sandwiching the infrared brane with B prime. And this is a nice way to sort of characterize what sort of constraints on RG flow follow from the existence of some topological structures. For example, there are some nice papers written about what are the consequences of what happens if I have a two-dimensional quantum field theory with a fusion category of defects, and I turn on a deformation which preserves that fusion category. The RG flow you often cannot land on a completely trivial phase, because somehow you need a representation of these topological defects. And a good way to understand it is in terms of these sandwiches. Anyway, I would like to use the last few minutes to describe the notion of condensation, which I developed with Theo Johnson-Freid some time ago. I think Theo will also use it in his talk. So the notion of condensation is born essentially as a generalization of the notion of gauging. In particular, a bit a posteriori, you can recognize some of the actions we were looking for as generalizations of the properties of the Dirichlet boundary conditions. So one of the basic properties of the Dirichlet boundary conditions is that you can use them to cut and paste gauge theories. So if I want to study a gauge theory on space, I can do things like I gauge the symmetry, but only on the positive real along the positive real axis, or I gauge it, but only along the negative real axis. Then how do I get, if I've done these two things and I want to gauge everything, I only need to gauge it on at zero, at the interface between these two regions. So sort of gauging is an operation which has this nice property. I can do it sort of in open patches, and then I can zip it together by gauging by using lower dimensional gauge fields. So to generalize this notion, we can do the following. Suppose that I have some quantum field theory or some system. Really, the notion is not specific to quantum field theory. It applies in a wide variety of situations, from topological phases to quantum field theories to lattice systems. So I want to say that I have a condensation of X to Y if I'm given with the following data: an interface from X to Y, a topological interface from X to Y, a topological interface from Y to X, and I want the composition of this interface. It goes from Y to X and back to Y, to admit a condensation to the identity interface for Y. So the definition of condensation is recursive. To understand condensations in dimension 3, you first understand them in dimension 2, and to do that you need to understand in dimension 1, and to do that you need to understand in dimension 0. And essentially, in dimension 1, a condensation is pretty much a projection, and in dimension 0 is essentially an equality. And building up in higher and higher dimension, you get more and more complicated definitions. but in a systematic way. So this definition works in any dimension, which is nice. Now, the basic nice property of this condensation is that if you compose the interfaces in the opposite order, to go from X to Y and back to X, you get an interface in the original phase, in the X phase, with a property that if you proliferate this interface, you can transform X into Y. So it gives you ways to do a topological manipulation mapping X to Y, analogous to turning on some gauge fields. To look at the analogy more carefully, let me look at condensations which are gaugings. So let me take a theory with G global symmetry and a theory where the global symmetry has been gauged. These are my X and my Y. I can define interfaces from X to Y and from Y to X as Dirichlet boundary conditions. So I say, okay, I have my X with G global symmetry, and I gauge G only on the positive half plane to transform it so that this becomes Y. Or I gauge it only on the negative half plane, and I get the other interface. Now, what happens if I compose these interfaces? I get a situation where G has been gauged on the left half plane, positive half plane, and on the negative half plane. And so to gauge it everywhere, I just need to gauge it along the interface between them. So again, recursively, if I believe that condensations in dimension Z, gauging in dimension 0 is a condensation, then it will be a condensation in dimension 1, dimension 2, dimension 3, dimension 4, and so on. And in particular, gauging in one dimension is the same as projecting on the gauge invariant states. So it's a projector, so it's a condensation. And so all gaugings are forms of condensation. If you compose the interfaces in the opposite way, to go from X to Y to X, you get a situation where you have gauged the G gauge field, the G symmetry only on a thin strip. And if you stare at it long enough, you can convince yourself that the resulting interface is really just the sum of all the interfaces which implement the G action. So in a sense, it's like so this condensation algebra, we call it, contains in this case all the information you need to study the gauging. So if you proliferate this condensation algebra, you're essentially summing over flat connections for G, you're gauging. I think there was a question from Nati.
Yeah.
Yes, I don't understand why you call it. I understand what gauging is, and I understand your description of gauging in terms of interfaces. What I don't understand is why this is called condensation. In what sense is this condensation?
Well, so there was a notion of anion condensation.
Well, my problem was already there. What I do understand is the gauging of the one-form global symmetry. And some people like to think of it as anion condensation, and I think I even talked to you about that. I don't really see in what sense this is condensation, and definitely not of anions. So, well, I don't see how your slide here addresses this question.
Well, it's in this proliferating, where is it? This condensation algebra. So when you have this structure,
for me, condensation is that I vary some parameter in the Lagrangian, and as a result, some order parameter gets an expectation value.
Yes.
I don't see why this is related, how this is related to what you're using, what you're saying here.
So in order to get Y from X, I would need to do the following. I take my X phase and I sort of draw a mesoscopic lattice of defects. And then I add some Hamiltonian, so I get a much more complicated thing. And then I add some extra terms to the Hamiltonian, which simplifies it to Y. I can at least imagine that a situation where some dynamical degrees of freedom that look like these defects become light might produce a similar result. So I think the only sense in which I would try to, so I don't know if this actually happens, but I can imagine at least that a situation where these defects become light, they proliferate, and so they start implementing the same modification of the system, which I will be doing.
If you want to keep it at this vague level, I have no problem. But if I have pragmatically say SU2 level 10, plus 1 dimensions, there I can gauge a one-point global symmetry and gauge SU2 SO3 with some level. It depends on how you normalize. I don't see how to do that by varying parameters in the Lagrangian and do that.
Definitely not with the original Lagrangian, but perhaps if I could add matter which transforms in the same representation which you're trying to condense.
No, then it won't work.
No?
No. U1 level, my favorite example is U1 level 8. Upon this procedure can go to U1 level 2.
Yes.
If you add the field with charge 4, it will just Higgs it down. It's not going to do the operation you're doing.
Yes.
Probably.
It's completely. She didn't finish the sentence, but I think she's right about that. So I'm going to mute myself.
Yeah, so sorry.
Yeah, so it's a name.
Please discuss later on in the breakout rooms. Yeah.
Yes. So let me just discuss very, very briefly an interesting application to topological quantum field theory. So we know that this sort of pure gauge theories, pure discrete gauge theories are a very nice source of topological phases, like Dirac-Witten theories. And so the most natural thing to do once you're given the notion of condensation is to look at pure condensation theories, which are sort of theories obtained from condensation from the trivial phase. In the same way as a pure gauge theory is obtained by gauging a G-symmetry of the trivial phase. This gives you a large, nice class of topological phases. And with Theo, we sort of argue that it's a very natural class. It sort of both satisfies all sort of nice mathematical axioms from axiomatized topological field theory, but also comes equipped naturally with a lattice construction. It really seems to describe generally all sorts of topological phases of matter or of field theories, which admit a topological boundary condition, a gap boundary condition. Sort of all sort of generalization of 2 zero in various dimensions. And I think Theo will use it in his talk. Okay, I'm done.
Yeah, I guess we have a lot of questions during the talk already. Is there some very short question? Well, actually, we have a big break, isn't it? Let me check out. Yeah, we have a break until like 5:30. Yeah, like a medium question is fine too. I'm sorry to I sort of being very like careful at the beginning of the conference. Any questions? Oh, okay. I hope my careful attitude didn't kill people's enthusiastic discussion. Yeah, so there. So I guess I leave further discussions to the breakout rooms. I guess David, do you want to take the second room? You want to be the same room as Shagang?
Sure.
Oh, okay.
Sorry, can I ask a question?
Sure.
I wanna know why you when you're explaining this T and T prime, you exploded to on the one side it's sort of dynamical in the sense, or maybe gapless. Is that what you mean? Mm-hmm. The other side is topological. But in general, you cannot do that, right? Because that depends on, because this situation will work if and only if the bulk is the chiral in some sense. That means it allows a gap the boundary. But in general, you don't have that, right? For example, like quantum Hall, or you have a topological protected.
But I never asked for the bulk to be generic, right? So my starting point was the theory in D dimension. I was asking if I can blow it up to a slab in D+1 dimension.
But I think for even for that gapless case, I think the argument for a lot of things can be moved to the to be considered topological still works, I believe, even in that case without the gapless boundary.
Mm-hmm.
Like in quantum Hall, or like the boundary of Chen-Simon. You can still sort of treat that as sort of a, you have some kind of a local data, which is what you call local dynamics, but then all the local dynamics governed by the say vertex operator, Cairo one, and then
Sure.
all the other things can be sort of topological.
I was describing two theories in D-dimensions, but most of the considerations would also apply to dynamical systems in D-dimension, which were already living at the boundary of something.
Yeah. Okay.
You know what? I probably just leave it like this. Whomever who wants to go ahead to talk to David, just do this. And at the same time, I'm making Anton a co-host and prepare the slide with it. Okay. So let's see. Let's try to see whether this way works better. Okay, co-host. Yes, so at the beginning, it's like we sort of want to promote discussion because it's a sort of new emerging area, but at the same time, to be careful of a certain order, but maybe sometimes I'm too careful, and
Can I ask a question since we have plenty of time here? So Davide, in your last slide, you talk about various a certain class of theories that can come from what you call condensing the trivial theory.
Mm-hmm.
So suppose I just hand you some abstract TQFT. How do you check if that TQFT belongs to this class? Can you give us more details?
Well, the first question would be to find if it admits a gap boundary. Right, that's the first step.
Yes.
Can I find a gap boundary? Can I cut the system, right?
Right.
And then the question is, can I heal the cut?
Mm-hmm.
So can I find ways for this cut to end in higher and higher dimension in such a way that I can reconstruct the theory in the absence of the cut? I think that as long as the boundary condition is sufficiently generic, this can be done. But I don't have a theorem. So I expect that pretty much having a gap boundary should be sufficient to belong to this class.
Mm-hmm.
But I'm not certain.
Okay.
I mean, part of the problem is, defining what did you mean when you said that you had a topological order. Clearly, for a lot of my considerations to apply, I need to be able to define topological defects and to move them without trouble. A lot of systems, like, I don't know, some fractals might admit a boundary condition, but might not be able to deform it without changing the properties of the system dramatically.
Mm-hmm. Mm-hmm. All right, thank you.
Mm-hmm. Right. There's a raised hand.
Can I ask a question?
Yes.
Hi. So I have a question. This concept of condensation, can I think it just as the gauging of topological defects, possibly non-invertible, at least in 1+1 dimension?
I think so. It should include that too.
And does it also include something beyond this?
Well, as I said, probably not. I mean, in a sense, like as I said, I expect the new theory to be something that I can obtain by proliferating the condensation algebra defect. So it is definitely, gauging a general defect.
Topological defect, right?
Yes, topological.
Thank you.
So as far as Samuel, you want to share the same room to discuss with people with Xiaogang all together. Is that the case? And then how?
Okay for me. I don't know what Xiaogang.
Xiaogang didn't say no, so usually it's fine. So let's do that because it seems like your tour has really a lot of interaction with his tour, and that might be a good idea. So everybody,
there is nobody in the rooms.
Oh, come on. There are so many questions. So everybody, so Xiaogang and David will be the room 1, and well.
Okay, so do we need to actually log into room 1 now, or is it?
No. I think, well, I'm not very good in this digital thing on computer, but I think, as Nikita told me, he will open something at 6:30 after Anton's talk.
That's what you meant. Sorry, I understand.
Right. Then we need to, I send you all this email with 4 links. Then you need to click on something, click on the section 1 thing.
Okay, I understand.
Yeah, and show up over there. And I also don't know like how this. We'll see the dynamics after a couple of days, maybe later on it's just easier just to have one thing. At the beginning I was afraid that when there are like too many people, 200 people, then some people dare not to ask questions, to have private chat with the speakers. On the other hand, I mean, speaker might also have fear that no one come to his room, but David, you should not be afraid. I think, there's so many questions, and as any point you feel like one room is too crowded for both of you and Xiaogang, then you can go to another room, and it's provided in the link. That I also don't know. Let's see the dynamic. Yeah. Okay. Great. So I just leave it over here. Whomever who wants to ask you questions. Just imagine you guys are in a lecture hall, and yeah.
So for the question about local dynamics and orbifolds from Nati, if the theory is massive, I think it's clear that the scattering matrix in the two theories will be the same. For example, just to give an example of in which sense they would have the same local dynamics. and I mean, of course, as soon as you start deforming one of the two theories by operators which are not available in the other, then the correspondence will break.
May I ask a question about the gauging?
Yes.
Yeah. So in my mind, when I think about gauging, for example, when I gauge the one-phone G2 symmetry, I try to couple the system to the background two-phone field, and I require this two-phone field to be flat. And we also need to require we condense the excitation of this two-phone field. So this is the requirement for gauging. So how is this picture related to the your talk in your way talking about condensation? So I think, yeah, maybe it's related to Nate's question. So in your description, the this procedure is not clear to me. So how do I compare to this picture in my mind?
Right, so for any discrete gauge theory, you have Dirichlet boundary conditions. Which are topological. At Dirichlet boundary conditions, the gauge symmetry becomes again a global symmetry. This is pretty much all that you need. So once you have Dirichlet boundary conditions, you can use them to define these interfaces and show that the gauging is a condensation.
So in this boundary, it's kind of you couple it to the, for example, you have a D2 degree freedom on vertex, and you couple to some D2 degree freedom on the link, and so it's at this place you condense the excitation in a higher dimension. Is it true?
Sorry, I need to visualize it. So yeah. A way to think about it is, gauge theory means summing over flat connections. Dirichlet boundary conditions means that you fix the value of the flat connection at the boundary. And the only equivalents that you use are gauge transformations which go to the identity at the boundary. This is the definition. So you restrict the gauge group to be the identity at the boundary, and you restrict your flat connection to a specific value when restricted to the boundary.
Okay, thank you.
Wonder how do I stop being a co-host? So is there a raised hand? I mean, if you have any questions, just go ahead and ask.
Hi, Anton. Do you want to share your slide now? There is a question. Hi. Hi, Yun An. I cannot hear you.
Oh, I have finished my question. Sorry, I should be.
Okay. So let me see, what can I do?
Oh.
Hi, we can hear you. Everything is fine.
Okay,
Yeah,
good.
we can see you too, right?
Just start sharing.
Yeah.
Screen. Okay. I guess you can see it, right?
Yes, we can see it. Thank you.
Very good. Okay.
So the third talk of this afternoon, I hope everyone is still it's very early in California, but probably it's already very late in Asia. But okay, so Anton, please.
Thank you. Yeah, it's pretty early in California, but luckily I get up fairly early too. Let's see. Yeah, so I changed the title of the talk at the last moment because I think I decided to change the content a little bit in view of the developments of the last couple months. But it's basically about the same thing with some additions.
One of the people are saying that is it possible to have a copy of your notes?
Yeah, I'll share the notes. No problem. Yeah, I guess I'll just send it to you. Well, in this talk I want to discuss the relation between physics of gapped many-body systems and topological quantum field theory. And by many-body physics, I mean physics of infinite volume systems, typical on the lattice, because just continuum systems are too hard. This is called, compared to systems with a finite dimensional Hilbert space, there are some important similarly technical things, but also which lead to important physical consequences. Like, for example, you can have sharp phase transitions as one of various parameters. And a related thing, one can have spontaneous symmetry breaking. That leads.
I'm sorry. I think people mean that could you, like last talks, share the PDF now in the already now so that they can look back during the talk.
Let's see.
You can also say no if it's too complicated.
But yeah, so how do I do this?
Oh, so
we don't actually have a PDF. It's a good notes. It's a pretty big file.
okay, then yeah. So we know it's difficult. Then just do it afterwards. No problem. Yeah.
I have to do it afterwards. Yeah.
Yeah.
Say I can convert it to PDF, but I don't want to deal with it
No
now.
problem. Yeah, no problem.
Okay, so that leads to like various interesting phase diagrams. That is, the behavior of systems changes discontinuously as you vary some parameters of the Hamiltonian or parameters of the like temperature. So here are two typical phase diagrams. So the first one is a ferromagnet. So you have let's see. So yeah, the first one is a sorry. So, yeah, so this one is a ferromagnet, and this one is a phase diagram of water. And as you can see, there are first order lines, transition lines, which sometimes terminate by second order phase transitions, like this one here. So that's one feature. On the other hand, even though the phase diagrams may be different, sometimes there's some universality, which is another important feature. And for example, so it so happens that this point and this point, even though they arise totally different systems, they actually have identical physics at long distances. So now this is all a classical story, but we would like to study transitions at a zero temperature. This is a new area of research, and so in that case, moreover, I'm going to focus on not on phase transitions, which are kind of more complicated, but the actual phases, and ask what are possible phases at zero temperature. So, well, I call them quantum phases because their complexity comes from quantum fluctuations, and the most basic distinction is just that we have gapless phases and there are gapped phases. And following the idea that I don't want to solve hard problems, let me look at gapped phases, which is simpler in some sense. Now, and then the gapped phases here, so they in turn can be subdivided into long-range entangled phases and short-range entangled phases. And what does it mean? Well, that's not so easy to define. So gap is easy to define. So what is a gap versus gapless? Well, gapped means you look at the Hamiltonian, in the infinite volume, and I insist on working in infinite volume always. In infinite volume, there is a unique ground state which you focus on, and then you look at excitations about this state, local excitations, and you find that if you find that all excitations have some minimum energy, then it's a gapped phase, and if some local excitations which have arbitrarily small energy, then it's a gapless phase. That's pretty simple. Well, the distinction between long-range entangled and short-range entangled, that's still a matter of debate what exactly is meant here. There are various proposals how to define this. For example, one idea I'll mention later also is that, is that you can basically ignore the Hamiltonian and just focus on the ground state wave function, and you can tell the difference between long-range entangled and short-range entangled just by staring at the ground state wave function, which is definitely not the case. If you want to try to tell gapped from gapless, that's might be harder because what I said is involves looking at the actual Hamiltonian and its eigenstates. Now, well, I'll discuss later what I mean at least by short-range entangled ones. But the long-range entangled case is actually hard, and it will not. I'll try to avoid any fine distinction of the long-range entangled case because, well, there's some simple cases like phases with broken discrete symmetry, which are familiar even from the classical von Donn-Ginsburg paradigm. Well, these are easy, but topologically ordered phases, which were discovered like maybe 30 years ago, and the first one being fractional quantum Hall effect. So they're much more complicated to describe in a precise way. And then there can be some combinations, but also There can be other things which are not topologically ordered in any conventional sense. For example, recently discovered fractons seem to belong to that catch-all category, which I've put question marks, described by question marks.
There's a question of Tail.
Yes.
Hi, Tail.
Yeah, I just wanted to ask you, I might have misheard, but I wanted to, you said when you said gapped, you said there should be a unique ground state at long ranges, and I've sometimes heard definitions with that, and I've sometimes heard definitions that tolerate like finitely many ground states.
Yeah, that's a distinction between working in a large but finite volume and working in strictly infinite volume. So in infinite volume, I think can also assume that you have a unique ground state. So working in finite volume has its advantages, but on the other hand, in the finite volume, you cannot have a sharp distinction between different phases because you have a mathematical
So I mean,
sharp.
I'm new to the field, but I thought like toric code was supposed to be the typical example, and I thought it had some number of ground states that was like 2 to the genus.
Yes, on a torus. But if you ask, okay, what happens if you take the limit of infinite volume? And all these ground states become the same ground states in the infinite volume. There is no observed, well, yeah, it's the same state in the infinite volume.
So infinite volume, you mean like the infinite plane, not?
Yes. Yeah. So on a plane, there's only unique translation invariant ground state. Okay. So now this is all very complicated, and one outstanding question is, can one use quantum field theory, for example, to describe all these phases? That would be a great simplification. Quantum field theory is easier than lattice systems because it describes, well, especially by definition, designed to describe long distance physics, but it's rather non-obvious if one can do it. In fact, for gapped phases, it seems like, well, with the traditional definition of quantum field theory that you learn as an undergraduate or first year in graduate school, it doesn't seem to work at all, right? Because quantum field theory describes particles, and there are no, like, at really long distances, there are no particles left in topologically ordered phases. They all become of too high energy. Now, of course, we know that nowadays we know that at least topologically ordered phases can be described by some topological quantum field theory, which does capture things like some features of the long distance physics. But it's not so easy to say what exactly it captures if you insist on working in infinite volume. Now, it becomes even more subtle if you look at short-range entangled phases, but the belief is that, again, short-range entangled phases, whatever they are, can be described by almost trivial topological quantum field theory. And almost trivial, but then I mean invertible. So I'll not try to give a precise definition of invertible to QFT, I'll just say which features it has from a physical viewpoint. First of all, topological field theory in general assigns some vector space to a closed manifold of dimension d. By d I mean dimension of space. In this talk, I always mean by d I mean dimension of space. So dimension of space then is going to be d plus 1. So any TQFT assigns some vector space to a d-dimensional closed manifold. And the special thing about invertible TQFT is that these unique ground state in physics lingo, in other words, that the vector space assigned to any closed spatial slice is one-dimensional. So that's kind of not very well. That's kind of difficult to phrase in language of systems and infinite volume. But something which is easier to say is that there are no non-trivial anyons. That is, non-trivial. Well, by anyons, I mean, first of all, anyons in the two-dimensional case, there is some particles with fractional statistics, but more generally, I mean some localized states which lie in non-trivial superselection sectors. So they don't have to be particles. In higher dimensions, they can also be strings or some other objects. So in invertible TQFT, there are none of this at all. So because of these two properties, they're almost indistinguishable from a trivial TQFT. In fact, the only thing which distinguishes them from a trivial TQFT is that the partition function is not zero. It's not partition function is not 1. Namely, partition function is non-zero for any closed Euclidean space, but it's not 1. So, and that's the only thing essentially which distinguishes them from trivial TQFT. Now, happily, unitary invertible TQFTs are much simpler than general TQFTs, which are like, well, you cannot classify them in any reasonable way, even in 2 dimensions. But unitary invertible TQFTs have been classified by Fried and Hopkins, and they are completely determined actually by these partition functions. So one can describe a TQFT, thanks to this result, simply by writing down the partition function of that TQFT. Now, of course, it's not arbitrary function of closed spatial slices. There are some axioms should satisfy, and Fried and Hopkins describe what's required from them. But one can express in terms of some requirement in terms of Bordism theory. But I'm not going to get into this in these talks. I'll just give an example. So, say there's some particular TQFT in 4 dimensions whose partition function is given by this, like just integral of the second Stiefel-Whitney class squared. Okay, so it's plus zx in this case just plus or minus 1, very close to trivial, but not quite trivial because it can be minus 1. Now, so on TQFTs, so invertible TQFT is well understood by now, but there's problems in relating them to short-range entangled phases. So it's believed that they're related, but it's not so easy to understand this, how to relate them. So first of all, what is a quantum phase to begin with? So in order to prove some theorems, in order to you need to first of all give a definition of a short-range entangled phase and more generally of a quantum phase. So there are some proposals in this direction, but there's nothing yet which can be mathematically rigorous. And more well, another thing which is not very conceptually is unclear is how would you ever compute this partition function that is which determines TQFT for any given short-range entangled phase? So because the point is that in condensed matter physics, you typically work either in infinite volume or on a torus. There's no way to even to make sense of statement like, well, put this or that system on a curved space. And if you're talking about putting on a general space-time manifold, Euclidean space, that completely makes no sense whatsoever. So if our definition of TQFT is the partition function Zx, then first of all, we cannot even check that a given short-range entangled phase corresponds to a particular topological field theory. And going backwards, if you specify some particular TQFT, which is not very hard to do, it's very difficult to actually even figure out whether a particular TQFT can be realized by a short-range entangled phase. So it's not clear how to map in either way, and it's not clear that maps are well defined. But we'd like to understand this because TQFT picture is very predictive. So one can think of, if you wish, relation between topological field theory and quantum statistical mechanics of lattice systems. It's kind of like in a way similar to relation between string theory and mathematics. So sort of TQFT makes predictions, and then you have to go and verify them, just in the world of statistical mechanics. Now, very rough answers to these questions are, well, the first 2 questions is that a quantum phase is an equivalence class of gap lattice Hamiltonians, and a short-range entangled phase is just a phase which is invertible. I'll discuss later what this means. Well, but the answer to the 3rd question is wide open. So we do not know how to relate TQFTs and lattice systems in general, and can hope they're related, but for now we're just reduced to checking some predictions of TQFT. Now here's an example which is quite famous, but still not well, still hides some complexities. Hall conductance at 0 temperature. Well, quantum Hall system exhibiting quantum Hall effect at 0 temperature, of course, were the first examples of quantum phases, which are not, which go beyond Landau-Ginzburg paradigm. And so let me remind you what the expected properties are. So expected properties for, so for this Hall conductance is that, first of all, you can define Hall conductance for any gapped system with a U1 symmetry. And this is actually a numerical invariant of a gapped phase. It's as you, if you replace your system with an equivalent system, by equivalent I mean equivalent in that yet undefined way. So they define the same phase. They're in the same phase. So the Hall conductance is supposed to be unchanged. It's a numerical invariant of a phase in 2 dimensions. Sorry, but say when I said any gap system, I guess I meant any gapped 2-dimensional system. Second, it's an abstraction to having a gapped edge. That is, if this numerical invariant is non-zero, then there is no way to have a interface between any system of this sort and a trivial system with a vanishing Hall conductance. No gapped interface is possible. Third property is that if you look at, well, this is so far for general gapped system in 2 dimensions. Well, general meaning general with U1 symmetry. Now, for short-range entangled systems, this Hall conductance is quantized, supposedly. Moreover, well, you can see quantized meaning it's integer multiple of e squared over h. And more interesting, even more specifically for bosonic short-range entangled phases, is actually an even. Quantized is units is even multiple of e squared over h. Now, these last 2 properties are quite, well, mysterious from the not easy to prove from the gapped lattice system perspective, but they easily follow from TQFT. So they realized early on that well, first of all, it's not a usual TQFT. So there's you need to specify background geometry, but you also have to specify background or classical U1 gauge field. And the partition function, well, let's just focus on dependence on this gauge field and ignore the dependence on the geometry. Well, in that case, the partition function is just given by the exponential at Chern-Simons section right here. Well, if you prefer, you can also, well, it's a bit ill-defined in the sense that A is not a 1 form. So dA is a closed 2 form, while the gauge field A is only, well, it's not really a 1 form, it's only 1 form locally. So the meaning of ADA is not very clear. But one way to make sense of it is to say, well, let's pick some 4 manifold whose boundary is X. Let's extend gauge field, well, the bundle in the gauge field to this 4 manifold X, 4 manifold Y, and then you can write some expression like that. And then one can show, well, under certain conditions, well, this doesn't depend on the choice of this Y and the way you extended the gauge field from X to Y. So anyway, so from the TQFT viewpoint, well, this is the partition function, and then the Hall conductance is identified with this coefficient here, and the reason it's integer is very simple, because otherwise your partition function won't even be gauge invariant. Or if you wish, this definition would depend on the choice of the extension of the gauge field to the 4-dimensional space Y. Well, if you look at in more detail, then it turns out actually that unless n is even, this partition function actually depends on choice of spin structure on your manifold X. That's because when you check the independence, you need to, well, turns out that if it's n is even, everything is fine. But if n is odd, you have to fix a spin structure on X, and then when you choose Y, you have to choose Y to be on spin manifold such that the spin structure on Y is compatible with spin structure on X. So the result is that the partition function actually does depend on spin structure. So you don't want that to happen in a bosonic theory. So presumably in a bosonic theory, n has to be even. That's all very nice and simple, relatively simple, but well, proving that directly from the definition of what a lattice system is, it seems very hard. So hopefully I'll get to how it's done in the last lecture. Okay, so now, so this was the introductory part, and now let me try to get into the more details of what I mean by by quantum lattice system with the energy gap, and what exactly I would like to prove about them. So, well, the big problem is to define and classify possible phases of lattice systems, but of course we'll only focus on gapped ones because others are too hard anyway. It's still a very big goal. So first of all, what do I mean by lattice? Well, first of all, I'm going to work in infinite volume, so I'm going to have my lattice is also going to sit in Euclidean space R sub d, and lattice is going to be just some countable subset, which is uniformly discrete, meaning there are no accumulation points. There's some minimal, and moreover, there's some minimal distance between all points. There's some there's some delta greater than 0, such that the distance between any 2 points of lambda is greater than delta. So there's no translation symmetry a priori. Now, second, instead of what's just a geometry of the system? So what about the observables or Hilbert space? Well, it's easy to say what the observables are. So I'm going to work with much easier to work with the sort of what's called spin systems. That is, to have finite dimensional observables on each side, which means that your algebra observables is a product over all points of the lattice. So P will label points of the lattice, and each of these local factors is just a matrix algebra. Now, while there's some subtleties here, well, each of these algebras is finite dimensional, but the product, of course, is an infinite dimensional. And but let's ignore them for now. So in the end, A is going to be a C-star algebra. Basically, take a sort of limit. You take first product over a finite region, then take the limit when the region gets bigger and bigger. And in this algebra, it's just some sort of C-star algebra, but it has some interesting substructure. Like if you just take product over some x, subset x in lambda, then you get some other C-star algebra, which is a subalgebra of this big A. So this notion of an observable localized on a subset, namely an observable which is element of this AOX. Okay, so there are, of course, also continuum systems, as well as systems with infinite dimensional on-site algebra observables. These are harder to deal with. I'm going to ignore them in this talk. So it's quite conceivable that they give rise to a very non-trivial generalization of this whole story. But the story I'm going to tell is non-trivial enough for me. Now, next we need to specify the Hamiltonian. Now that's a bit problematic. So a Hamiltonian is a formal sum for now of just some interactions. So I sort of subdivide my Hamiltonian into pieces, and each piece is local. Well, the simplest version would just say that each piece is belongs to this local algebras of observables localized on some ball of some radius r around the point P. So now this is not like absolutely necessary, just a convenient restriction, easy to say. This kind of Hamiltonian is called finite range Hamiltonians because each term only acts non-trivially or commutes non-trivially with the observables on some finite ball around some particular point. Now, there's a sharp distinction, physical distinction between systems with long-range interactions and systems with short-range interactions. But short-range usually, short-range interaction that usually means interaction which decays fast enough So here I sort of oversimplified by saying the direction is literally 0 beyond some radius. So exponential decay would be good enough, and in fact, it's more convenient for my purposes. Just don't want to get into technical details at this stage. So, well, as we want to study ground states of such Hamiltonians in infinite volume, that is, on some infinite lattice, and we'd like to understand them up to classify them up to equivalence, of which I haven't said what it is. Now, one important point, actually the crucial point for what follows, is that the Hilbert space where this Hamiltonian acts is not specified from the outset. It's extremely important in this whole business, and actually in the whole of quantum statistical mechanics, that you can only construct the Hilbert space once you know what the ground state is. It's kind of funny, but actually there's a way to say what is a ground state of a Hamiltonian without saying what the Hilbert space is. So a state will be just some linear functional on the C-star algebra observables, which is in some way compatible with the Hamiltonian. I'm not going to say now in which way, but once you found such a state, or somebody just gave you that state, then you can construct the Hilbert space using the Gelfand-Naimark-Siegel construction. And then you can realize your abstract C-star algebra by operators, by bounded operators in that Hilbert space.
Anton, I just have a question about your Hamiltonian on the previous slide.
Yeah.
Are all of your dimensions of the spaces on each site the same, or are they different?
No, they can be different. They're not restricted in any way, actually.
So what do you mean by Hamiltonian if they're different? Are you thinking of this as a Hamiltonian as taking from one Hilbert space of one dimension to another?
No, so first of all, Hamiltonian is a formal sum of elements of the C-star algebra.
So you're only thinking of these Hamiltonians as acting on a single vertex, correct?
No. Hamiltonian acts in some neighborhood of the vertex. So as you can see, it's element of this algebra A, the subscript BP of R, which is and BP of R is a
it acts on the tensor product of all of them.
Radius R and center at P. So A acts on some sites around P. So HP acts on some sites around P, but within some finite radius. And then you take this infinite sum and you get this Hamiltonian. So so H is kind of funny thing. It's not an observable by itself. It's an infinite sum of observables. And it's not an element of the C-star algebra. So what is it for? Well, technically, you can use this Hamiltonian to define evolution on this C-star algebra, make it a dynamical system. So the corresponding unitary evolution operator is a well-defined automorphism of the C-star algebra. And then you proceed from that. So that's how it's a bit roundabout. Yeah. So, well, yeah, that was a very general setup, by the way. And if you want more details, there's a monograph by Bratelli and Robinson, which is basically the only exposition in a detailed form of this formalism. There's lots of details about that. Now, so now let me return to this issue of gapped versus gapless. I want to say more exactly what I mean by gapped phase, or gapped system, sorry, for now. No phases yet. So, well, a gapped system just means that if you go through this procedure and you get your Hilbert space and you get representation of the algebra observables, then H, that abstract sum, becomes, well, that's a bit of a poetic what I'm saying here. That's not quite genetic representation maps elements of the C-star algebra to bounded operators. Our H wasn't even an element of the C-star algebra, but in some sense, it does give rise to an unbounded operator on the Hilbert space, which you call H hat. And well, by definition, essentially, the ground state, which is going to be just some vector in this Hilbert space, is annihilated by this H hat. And by definition, the operator H hat is positive. And what we want is that the spectrum of this self-adjoint of this operator H hat has a gap between 0 and excited states. So that's what gap means. And so that's the setup. And our desire is to classify such Hamiltonians, well, and also algebras, up to some equivalence, which I haven't stated yet. And we'll get into that later, much later. So that's actually very hard. And I'm not really going to touch the classification in this talk either, but I'll try at least to explain how to construct some invariants of these equivalence classes, some numerical invariants or something similar. Yes, numerical equivalence. So I'll call them topological invariants. They're really numerical characteristics of a phase.
Can I ask a question?
Yes.
Well, could you please turn to your last slide?
Yep.
Yeah. So what do you mean by the Hilbert space is not specified? So we are not given any Hilbert space, right? Could you please explain this a little?
It's not specified from the outset. Like the point is that if you look at the construction of the algebra observables, you can construct it just from this local algebras simply by saying, well, if you have some, so basically take the limit, and your generic element is roughly something like a local observable on some ball extended to the times identities everywhere else, right? So it's sort of extend by identity away from some ball.
All right.
Now, but you cannot do this with Hilbert spaces, because if you start with Hilbert's, so the point is that in the matrix algebra, there's a special element, identity. If you start with some finite observable, you can make it observable in the whole infinite system just by extending by identity, with tensoring with identity. But with Hilbert spaces, that doesn't work, because there's no, I think, no distinguished element in the Hilbert space. Like each of these algebras acts naturally in some finite dimensional Hilbert space. But if you try to take tensor product over all Hilbert spaces, that makes no sense, because you don't know what to extend by. There's no like special vector. So as a result, you don't know which Hilbert spaces you have, what space you have. And it's okay, that's standard. You construct it afterwards, that's what I mean. Even though you don't have it in the definition of the problem, you construct it afterwards, but first you need to specify the ground state. So, and there is a way to say what a ground state is without, because there's a way to say what a state is without specifying the Hilbert space. You can just say state is a way to evaluate averages of observables, expectation values of arbitrary observables. And you can say what it means for that's just a state. It's possible to say what a pure state is just in this language. And it's possible to say what a ground state of a Hamiltonian is in this language too. It's just state invariant under evolution. And that can be said without specifying the Hilbert space. And once you have all that, you can stick into some machine called the Gelfand-Naimark-Siegel construction, which spits out a Hilbert space.
Okay. Okay, thanks.
Okay, it seems like a technical issue, but we'll see. Actually, it's extremely important.
Was there something similar as Chagall's talk, like taking the limit of this sequence, this Gelfand's?
Unfortunately, that was very early for me, so I didn't attend.
Oh, okay.
Yeah, but by the way, I recommend everybody who wants to like a hands-on explanation of why you need to go through this stuff. Read there's some famous paper on von Neumann which has infinite tensor products in the title. It's extremely pedestrian because it was way before people developed all this complicated technology. It was way before Gelfand, Naimark, and Siegel. So he goes in extreme detail explaining why taking infinite tensor products of Hilbert is just not a good thing, even if your individual Hilbert space is like two-dimensional, like a spin and a half Hilbert space. So it's extremely detailed and nicely written paper. So anyway, so let's think about, first of all, what it means to construct a numerical invariant of a gapped phase, whatever that phase is. Well, here's a bit poetic picture. We imagine that there is some space of Hamiltonians in a particular dimension. I call it M sub d. And imagine it's a sort of space, topological space. I want to say that if you deform the Hamiltonian a little bit without closing the gap, then it's still going to be in the same phase. It's a necessary condition, whatever, no matter how we define the equivalence relation. In the end, we want this condition to be satisfied. Deforming Hamiltonian without closing the gap should not lead to a new phase. So because of that, you can imagine that, say, all Hamiltonians in a trivial phase form some space. Here's one. And if you have some non-trivial phase, say short-range entangled phase, whatever it is, they form a different space. It's some horrible infinite dimensional space. And the point is there's no continuous way to like go from Hamiltonian here to Hamiltonian there, but you can freely move around within the space of all Hamiltonians in a trivial phase. Now, by the way, I drew all these pieces here, all these three pieces here, as having one whole, because actually all these spaces have identical topology. This spaces, no, if you have some, if the point is you can take composite of several systems. So if you take, say, any system in a trivial phase and tensor it or stack it or compose it with some particular short-range entangled system, then you're going to end up here or here in one of those other pieces. And as you vary your trivial system, you're just going to here, you're going to vary now your stacked one here. So this stacking with an inverted, with a short-range entangled phase gives you, it's supposed to give you some one-to-one map between these guys and these guys. So if you're just, well, so that's why I drew them in the same sort of shape. But if you look at topologically ordered systems, which say some other phase, and the system say form some other space of systems in a particular phase, that might have a different topology because there's no like a way to relate this with that, for example.
So just to confirm, each point in MD is this set of equivalence classes of systems that you...
No, each point is actual Hamiltonian, actual algebra in a Hamiltonian. Now, of course, I cannot vary algebra continuously, but imagine that, well, so I want to vary Hamiltonian and I want to vary algebra. Now, varying Hamiltonian sort of makes sense. Varying algebra continuously doesn't make sense, but I imagine that first I do it for different algebras, then somehow glued together so that you can talk about systems with different algebra observables being in the same phase. And then I end up with this, say, something like this. Okay. So that's a tricky part. I don't actually know how to do that.
Shouldn't we do everything with respect to a given algebra, which for some reason is the reasonable one?
Well, I think one can do it, but I think in the end, to get nice properties, to get something understandable, you'll have to, you know, like, well, I don't want to work with the, okay, physically, I think you do want to say that, you should be able to say that, say, systems with two different algebras or observables actually are in the same phase. Because if you just add some highly excited states to your system, this shouldn't matter. So you should be able to explain what it means for it to be in the same phase. So you need to have some equivalence relation which makes it systems with different algebras or observables, with different number of degrees of freedom per site, equivalent. You know, adding some high, you know, some orbitals with very high energy cannot change classification of phases. So you should be able to do that.
Can you give a concrete example of what you just said, where if you keep saying you have some lattice system, say with some spins, and all you need to do is change the parameters in the Hamiltonian, and you seem to imply that there is more than that, something associated with the algebra.
I'm just saying that if you just, like suppose you add some at some site, let's pick a site, maybe an infinite set of sites, and just add some degree of freedom, which has, say, only two states, but it's totally decoupled from the rest of the system. But say the one of the states has low energy 0 and the other state has very high energy. Right? You would say that, you know, whatever, if you do that, the new system is in the same phase because, you know, your states with low energy are going to be indistinguishable from the original system. You know, the extra stuff is just frozen in the ground state. But what does it mean to be in the same phase? Well, you need to be able to set up some equivalence relation, under which this, it's not just varying a Hamiltonian, because, you know, varying Hamiltonian, the number of degrees of freedom per side.
But you usually have the concept of Morita equivalence, right? Where you do just this, right?
It's something similar, yes, but we need like something physical, some physical definition of equivalence relation, which is similar to Morita equivalence. Yeah. Like in K theory, it's stabilization. We do it all the time. So, anyway, so having this picture in mind, you could say actually the set of gapped phases, and then just pi naught of the space of Hamiltonians in particular dimension. It's just labels these different pieces. Okay. Well, there's actually some further structure to this because you can work either with bosonic systems or systems which also involve fermions. So there are actually two different such spaces. There's a bosonic one, there's a fermionic one.
So I have a question about that. Is it clear that the pi naught is the same as the set of gap phases? Can it be that there are different phases that you cannot interpolate between one and the other, and you cannot characterize the difference between them by the usual observables?
Well, essentially, when I set it up so that this is true, okay. So this is since I haven't defined what this MD is, it's up to me how I define topology or on this set of Hamiltonians with different algebras. So I want to arrange definitions so that this is actually true. And I don't know what a phase is.
So this is true by definition?
Yes, that should be true by definition. And right now we don't have definition of either MD or what a phase is. Okay. Now, well, we do know, well, assuming this, well, this some non-rigorously, we do know something. For example, if fermionic phases in one dimension, then it's believed that pi naught is Z2. And there's a concrete representative of this non-trivial generator. It's so there are only two elements in this pi naught, and non-trivial one corresponds to the Kitaev chain. That's what's believed to be true. And it's believed that if you look at one-dimensional systems made of bosons, then it's all one big blob. They're no non-trivial phases. Well, unless you add symmetry, but here I'm suppressing symmetry. So we just suppose no symmetry. I'm allowed to break any symmetry. On the other hand, in two dimensions, believed that there is, sorry, I guess should have said that it's sorry, this is only for short-range tangled ones. So in two dimensions, it's believed that if you just focus on the short-range tangled part of this big space, then there's only one invariant, the chiral central charge.
So I have again this question. So where does the torus come from, or this graph come from?
It's not torus. It's just some ramp. I could have put more holes. Yeah.
What does it represent?
It just the space itself might have some non-trivial topology. I don't know what it is. So I put some random number of holes. I chose one.
It's always two-dimensional? No.
No, it's just some. It's actually infinite, always infinite dimensional. I just still haven't learned how to draw infinite dimensional pictures. So
it's this Hilbert space. You mean?
No, what's infinite dimensional is space, actual space of systems, because they can have an infinite number of sides, an infinite number of terms in the Hamiltonians, like really infinite number of parameters you can vary.
It's the whole. Okay. It's the whole.
Okay,
that makes sense. Okay.
So that's why it's so difficult to work with this. So it seems completely actually undoable, but actually there's some things you can do. Now, and one thing which has been argued is that this, if you at least you focus on short-range entangled phases, whatever they are, then the spaces, then that piece is actually more comprehensible because all the space actually are related in different dimensions. Like if you look at the space of loops, well, in this space of short-range entangled phases, there is a particular system, the trivial system. Let's pick a trivial system there, and it's called a base point. And now we can look at loops and the space which begin and end at this special point. And you start with some space of systems, you look at loops and get another space called a loop space. Of course, even for a very simple manifold, loop space is going to be infinite dimensional. Well, here it's even worse. We start with an infinite dimensional space and take a loop space, and it's even more infinite dimensional, but okay, it just does make things worse. So the claim is that, Claire's claim is that if you take the loop space of the space of d-dimensional short-range entangled phases, you get actually something which is homotopy equivalent. I denoted with this, sorry. I denoted with this tilde. It's homotopy equivalent to the space of short-range entangled phases in one dimension less. And iterating this, you get that if you take k-fold loop space, in this d-dimensional MD, then you get something homotopy equivalent to space of phases in d minus k dimension. Well, mathematically, it means that they say that the spaces form a loop spectrum. Spectrum here has nothing to do with the spectrum of operators, it's just math terminology. Now, from the practical viewpoint, that will be very nice because that will actually constrain a lot the topology of these spaces. Because basic topological fact that, if you look at, say, we can just use basic topological fact that if you take a kth homotopy group of the k-fold loop space, the same as just pi naught of the original space. So then you see that the kth homotopy group of the space of d-dimensional SRE phases gets related to set of all d plus chi dimensional phases. So if you know something about so if you know something about sorry, it's wrong. D minus k, sorry. So it's with d minus k, sorry. So anyway, so it's, yeah, d minus k. So so there's some d minus k. Okay. So anyway, so this is just a conjecture, and which about this loop spectrum. What I really like to do is to sort of check this by concrete computations with lattice systems.
Do you have an explicit map relating the loop space of the d-dimensional entangled system?
No, it's all like with there's like hand waving arguments, but nothing precise.
Okay, thank you.
So I'd like to focus then on this not just a space of set of phases, but actually the set of the topology of these pieces, because that's something we can actually hope to access too. So suppose you have this space m sub d of, well, space of all phases for now. But let's focus on some connected components, say, for example, a trivial, corresponding to a trivial phase. So we'd like to know, say, what is homotopy groups and cohomology groups? And more generally, what is homotopy type? And how does one detect the non-trivial topology of the space concretely, if what sort of physical consequence it has? Now, the case which is very well understood but not very interesting is the case of d-dimensional systems. But let's see how it works there, just to see kind of model for the higher dimensional generalization. Well, so there, suppose you have a family of systems with a unique ground state. Well, it means you have a Hamiltonian depending on the parameter. And parameter, well, it can be a multi-dimensional parameter. It can take value on some manifold. So in this case, there's no problem just fixing Hilbert space from the outside, from the start. So it's going to be, well, so fix this Hilbert space, and we assume that the ground state is unique. So here you have to assume it again. Essentially, again, by definition, you want it to be unique. And then you solve the problem, you find the ground state, and you get a vector in this Hilbert space. And as you vary parameters, you get a line bundle, rank 1 vector bundle over this parameter space n. I call this bundle B. So Michael Berry noticed that there's actually canonical connection on this bundle. It's familiar construction. I'm not going to describe it, so connection is nabla, and its curvature, I'll call the Berry curvature, is some closed two form, and moreover, its periods, that is integral over some closed two-dimensional manifolds, are 2 pi times an integer. So from the topological viewpoint, the cohomology class of this curvature is the first Chern class of this bundle B. And so if this class is non-trivial, then the family of Hamiltonians is topologically non-trivial. That is, it cannot be contracted to a constant family. So you start with a very trivial situation, that is your Hamiltonian, well, your ground state is unique, nothing interesting there, but you can vary the parameters in such a way that you get a family of this ground state, so that there's no way to deform this family to a constant family. And that can be detected by this class here, by this cohomology class here, if you wish, by the curvature itself. Although curvature itself does depend on various dynamical details, but the class doesn't. It's quantized after all. Like, moreover, this class, cohomology class, is actually completely invariant of a family. So what do I mean by this? We can start with this, with our thinking about this by thinking about Hamiltonians with a unique ground state. But Hamiltonians are actually not very important, because you can sort of deform the Hamiltonian to a much simpler Hamiltonian. It only has 2 eigenvalues, 0 and 1. So that the ground state, without changing the ground state by definition is going to have eigenvalue 0, but everything else, all excited state, is going to have eigenvalue 1. You can just sort of deform a Hamiltonian this way without closing the gap. So currently, you can say that the space is somewhat equivalent then to space of rank 1 projectors in your fixed Hilbert space. Well, it's the same as the well, homotopically it's the same as this. So, or you can just say space of lines. This just space of ground state itself is your space of interest. Now, this space is actually has very simple homotopy structure. So this projective unitary group of a Hilbert space, well, let's do infinite dimensional one, because even if it's not infinite from the start, you can imagine that it's embedded into some bigger one, and the rest just doesn't matter. So this space, it has a simple topology. It's what's called the Eilenberg-MacLane space, or KZ2. So it has a its homotopy groups are very simple, just 0 if k is not equal to 2, and z if k is equal to 2. So as a result, if you look at possible family of Hamiltonians, it's the same as a map from M to space of projectors, or equivalent to this space. So you get well, but the map from manifold to this KZ2 is just same as degree 2 cohomology class on M. So specifying a family of Hamiltonians homotopically is the same as specifying a degree 2 cohomology class. And this is precisely this class of the cohomology class of the Berry curvature. So the homotopically, there's no more to specifying a space of Hamiltonian, a set of family of Hamiltonians, than to specifying actually this class on the base. So that's what I mean by it's a complete invariant of the family. So so this well, so in the language of the previous slide, so essentially we showed that this space is just this KZ2 homotopically. If you assume this Kitaev's conjecture, then that immediately makes some predictions about higher dimensional guys. Namely, it tells you that say d-dimensional homotopy group of this space of short integral phases in d dimensions is actually just integers. Oops. Sorry, PD plus 2.
Did you assume that V is infinite dimensional?
Yes, because I would like to, like, if you don't do that, you get more complicated answers. And essentially, when I set up the problems, I can always add some degrees of freedom. and which I don't do anything, and then continue deforming my Hamiltonian in this bigger space. So that's one reason it's important to allow enlarging the space of degrees of freedom by adding more of them. So you can just take the viewpoint that, you know, the most complicated thing can do is to take infinite dimensional space from the start. Or you can just say, you know, I start with finite dimensional ones, but sort of when I don't want to deal with many different options for dimension. So I set up some equivalence relation, which says that Hamiltonian for some finite dimensional Hilbert space is identified with a Hamiltonian in a bigger Hilbert space, which is just the old Hamiltonian in the region, some subsector, and that's just something trivial, like say trivial get Hamiltonian in the for the remaining degrees of freedom. So in this case, I can sort of take a limit over dimensions on the Hilbert space, but taking a limit to infinity, I end up with the same topology, it turns out. So I might as well just start with infinite dimensional space from the start.
You're saying this is true even if you had an arbitrary lattice, like instead of associating to a matrix algebra, a finite...
There's no lattice here. It's all about 0 dimensions. We're not doing anything like this in hard, well, I don't know. In higher dimensions, we don't do that. Because in higher dimensions, that leads to complications. Maybe it should be done, but I don't know how to deal with infinite dimensional Hilbert space per lattice site, so I don't.
Can I ask you, which topology actually are you looking at? Is this the norm topology?
Yeah.
But all infinite dimensional projections are equivalent in the norm topology.
What do I mean equivalent? They're continuously connected. Yeah, so we're not talking about equivalence. Really. The point is that the non-trivial topology is the space of projections.
So here you have a unique ground state. So the projection, which is perpendicular to the ground state, is infinite dimensional.
No, yes. So it's projections on the projections here. Are so I want to look at the space of rays in infinite dimensional Hilbert space. That has a non-trivial topology.
In the norm topology?
Just the usual topology of the Hilbert space.
I don't.
So the unitary group has a trivial topology. That's true, it's contractible, but the projective unitary group has a non-trivial topology.
Can I ask a question?
Sure.
Why is UV over U1?
So it's not UV or U1. So I have to like also do the
UV -1, I think.
Yeah, so it should be like the orthogonal one too, but homotopically it doesn't matter.
Okay, thank you.
So shall we say like today's lecture is content-wise is here now, and okay, so there are some breakout sections, and I think people can join with people need to quit this link and join in another link, and over there we will not do the record, so you can feel free to discuss at ease. Okay,
so there's only one breakout room, or there's a 3 breakout room?
There are actually 4 breakout rooms, and Xiaogang, you know, I think
what's
you
the
can
arrangement?
choose.
You may make a decision, and we just follow.
Okay, I make a decision. I'm sorry, I make a decision. So for the first time, let me try my idea. like Xiaogang goes to the first breakout room, Devi go to the second, and Anton go to the third. Okay.
Sure.
And if I see that it doesn't work out, we will combine some breakout rooms.
Okay, sure.
Is that okay?
We'll do that.
Okay. Okay. Thank you. See you soon.